Okay, there we go. We're connected, we're going. So I'm gonna post this, and then we're gonna get going. Okay. Close this. Open up my code, which is a horrible mess right now. We have the paint pixels to global pixels here. And I believe that is the inverted command. I don't think we actually want to use this one. So the idea here is we have a put get test, and we want to check every single pixel to make sure that the conversion back and forth is correct. Or not the conversion back and forth is correct, but this is this is a put and get test for the main functionality. Okay. And the main functionality of this is one, AAC 2020 PAINT5D put, right? And two, AAC 2020 PAINT5D, guess what? Get. Alright, we put before we get. That is why the order is P for put, then G for get. And we have a lot of loose ends here, so it's going to take a while to get this up and running again, unfortunately. And we did this to ourselves, and, you know, you should not do what I have done, but every once in a while you have so many loose ends, or so many things that need to be done, where, you know, you thought it was going to be a simple sprint, and there was only going to be a few pieces of code you needed to add, and it ends up just spiraling out of control like this to get to the next feature, right? So we're trying to sprint to the next feature, and we bit off too big of a chunk. And it seems like very commonly we're biting off too big of chunks. And the reason for that is, right, we're trying to focus on each sprint as one subsystem. And for each subsystem, we want it to be just a very small system that just does one thing and does one thing well. So we took off this big chunk of this one subsystem, and it ends up doing a little bit more. It's not that it does anything outside of its scope, but that it has keyboard binding logic in it, as well as conversion logic and whatnot, and it just got out of control. So with this function here, painpix to glockpix, this should really be called, and we can even see, this should be glockpix converted to painpix. And now we just need to change what's a pointer and what's not a pointer. And also, this is not even a proper function call here, because we stole it from the prototype. We want to take this, and we want to say, okay, what's supposed to be an address, and what's supposed to be just an input. And that's pretty easy to know, because we see that px and pay, that's pixel x and pixel y, that is going to be our global tx and ty. So those are not going to be addresses, but everything else is going to be an address, because they conceptually create our paint pixel location. Now, let's actually create some variables for px and py. The global tx and global ty, let's just declare everything here. Right? Let's declare all of these for a second up here, so we know kind of what we're doing, or we at least know the signatures. We need these declarations no matter what, but as we're thinking about things, it would be nice to, you know, actually have these here. So UO8s and I16s for these things here. All right, so we have a kind of a division here between what is right, so all of these technically make up these are all for this function here, right? So we could say So these are for, you know, this command here. And I don't know, right now I'm not feeling like putting trap values in these declarations. I don't think it's been helping me lately for this specific thing. Now that could come back to bite me, and, you know, maybe later we'll put some trap values in here. PX and PY. Let's define those. So we could just say, you know, let's just do int32, or you know what? Let's do U16, or no, let's use I16. Let's use the same type as these things here, and just say px for pixel x and I16 py for pixel y. So this is, you know, pixel x location, and this is pixel y location. And when we're talking about pixel x and pixel y locations, what are we talking about? Well, like, where is that data? Well, if we look at our diagram for PAINT5D, actually, we're going to need to look at, we're actually going to look at pixname here. So we have pixname, data. If we look at that, we can see this chunk called PAINT5D, CPU side pixels, and that is where this is. So we could make a little note here that px py equals glow tx glow ty, and is a pixel located. Right. We can kind of make that kind of short, right? px. Right. All right. So we can make a little note here about what px py is. Can't talk here. And we want to make a note that this is where it's located. So even though we may not have this variable referenced in code anywhere, we can make a note that, you know, that is what we're using. So, you know, at vid iid 0 hours 7 minutes and 54 seconds. Right, so this px py is equal to global tx global ty. Px py is located on this pixname allocation of CPU side pixels, which is a 512 by 512 bitmap. We can see it over here. That multiplication by 4 is because there are 4 bytes per pixel. There's R, G, B, and A for red, green, blue, and alpha, respectively. Ooh, that was bad. Okay, let's close this guy. Let's go down here and see how we're trying to manage this. So we're trying to go through the entire 512 by 512. You gotta remember that the last pixel is 511. That's why there's this -1, because we're doing an inclusive range. First thing we need to do is set glow tx equal to px and glow ty, global ty, equal to py, because these are input parameters. So we could say that for this, you know, load function inputs. Okay, these are inputs right here. That's why these ones do not have address operators on them, or address of operators, whatever you want to call them. Or I'm sure there's a proper name for them. Once we've ran this function, right, we've already tested this function at this point, right? Once we get to this get put test, we've already tested the components that are responsible for how do I say this? Let's see, get put. We've already, right? We have right. We're using glockpix to painpix, and we already have the test for this here. So now we can run this here, and in this get put test, we've already spot checked this. So this needs to be down here. So we have a very specific ordering for how we want to do these unit tests, right? We want to make sure that if some code depends on some other code, that the code that is dependent on is tested first before we code things that rely on it. And that's because when we find an error in our code, we want to make sure that we're looking in the correct place, right? Like, if you have a function that says runs the quadratic formula, and this is a very contrived example. Let's say you have a function that runs the quadratic formula, you test it, and it doesn't work, and it turns out it's because you have another function that does multiplication, and it does multiplication wrong, and it's actually that thing that's broken, and it's not your quadratic formula stuff. Then you want to test the dependency of that multiplication logic before you test the quadratic formula logic. That's a completely contrived example, but that's the idea here. So we have a very specific ordering of when these functions need to be called, right? So this, if you want to make a note, depends on, and it depends on, right? It depends on the get, it depends on the put, and it also depends on this PAINT5D to GlockPix. No, GlockPix to PAINT5D. If we want to make absolutely sure, and now we're kind of like out of room, and I would like to keep this kind of the full name so I can just kind of click them and see them. So let's just do this. At depth. So just hashtag with dependency, like at depth, so we can kind of see it. And then we're going to kind of section it off a little bit like this. And then we'll also kind of make a note of it. Right? So this is a little bit obnoxious where we had everything kind of nice and clean, but this one thing, I want to make absolutely sure that everything that depends on it is, in its proper place. So, we can do like a at vid IID and do 0071, that's the video ID, and the time is 0 hours, 12 minutes, and 52 seconds. Okay. And we can kind of, okay. So this function is going to depend on a lot of these other functions, these ones particularly, to be working before it runs, right? Now there's these are the most direct dependencies, but it also indirectly depends on basically everything here, right? So we only listed the dependencies that are kind of direct dependencies here, and we just do at dep to kind of know like what we mean by that. So we can make a note of this because I don't think we have this anywhere. And I don't know what we want to call it. I guess we could just do that, and that would be good enough for now. And we could do, a vid IID of 72, and the time, or not 72, 71, and a time of 0 hours, 14 minutes, and 18 seconds. So we're just going to use this at depth notation to be shorthand for depends on. And we don't really have a depends on notation. But depends on some function, right? We just want this kind of notation in our code in some places so that we can succinctly communicate when, this region of code, this thing, is depending on this, this, and this, right? Yeah. So now, as far as these other things, there are some logical groupings of these test functions we should think about here. So we have, like, min, that looks like a kind of a utility function. This is some type of conversion function. So right away, I'm looking at this and thinking to myself that I see we're testing this, and maybe these functions do not, these functions here, right up here, do not actually use these min and max functions. But the thing is these are definitely smaller functions in terms of their utility. They're like more granular functions. So we should probably put these tests first, right? And I don't know where they're being used, but we can kind of look around and see, well, where are you being used? Are you being used in these functions up here? Like maybe it is properly ordered, but even though it's properly ordered, it's like, so I don't even see this cap U32 being used anywhere, which is kind of scary, isn't it? Why are you not being used anywhere? So the first thought is that I named the function wrong, maybe? Oh, hold on. No, I'm just being stupid. This is the unit test function name, not the function name. So if we look at this, PAINT5D I32 cap U32, initialize PAINT5D, and we can see these are helper functions generic, and they are way at the top. After we got, like, you know, this boilerplate and then some initialization code, but then after that we have helper functions generic, and they are ordered before everything else, which makes sense. So in our test code here, I don't know why we have it here, because to me it looks like it really should be up at the top. But let's take a look at where min16 is used, and is it used in like any of our convert to functions? Because I bet Glockpix C2 PainPix. So it's not used in the. It doesn't look like it's used in these conversion functions here, but even so, we should probably just write the test functions based on the order that they appear in the code, right? Because the order these functions appear in the code, any of these functions, how they're written, they don't use forward declarations. So if we test our functions in the same exact order that they're declared, we won't actually have any dependency problems, because we have to declare them in dependency order in the first place. So let's take a look at this and actually give them the same kind of labels as the labels they have in the code, which could, you know, be something that might not be maintained, but we have helper functions generic. I would like to take this same section that says helper functions generic, and we have helper functions conversion, and it looks like just these two functions. Oh, we have like 3 functions here. Oh, we have 4 functions. Boy, we have a lot of functions. So let's go to here, and let's take that kind of label here. Helper functions generic. And can we kind of lowercase that and say, you know, make this kind of make it kind of like the same kind of section, but make it a little bit less bold, because we are inside of a test already, and we don't really want that bold line hierarchy in here. Like, we want to separate, we want to section off like where we are, but we don't want to be completely obnoxious about it. We want to maintain a hierarchy where we can tell, hey, we have a section, but this section is not like a different function, if that makes sense. So helper functions generic is these 2 functions, and then we also have a whole bunch more helper functions. I'm seeing like it's not just these 2. It's is it diagpix as well? Like, are these all, like, do we have these 3? I think these 3 are more detailed helper functions. So if we can kind of color these, I feel like there's something else missing that hasn't had a test written for it. So let's color these, and then let's just look for helper functions and be like, oh, we expect like these 3 colors, and not the generic functions, but the conversion functions. So we got this orange, and then we have this cyan, and then we have this yellow here, but we're missing tile exponent converted to diagonal pixels. And you'll see it's kind of this basic kind of lookup here, where it's not really something that is a big deal, where it's going to be hard to test, but we should for kind of complete coverage, put that in our code. So what we're going to do here is, I notice things are kind of out of order. So we're going to start a clipboard stack. And, no, not like that. CS start. We're going to start a clipboard stack. And we're going to take every one of the functions in this area called helper function conversion, right? So we'll go all the way up here, and we'll just take each one of these, right? So we'll take this guy here, copy it, then we'll take this right here, copy it, and then we'll take this one right here, and we'll also copy it, and then the last one right here, we'll take this as well and copy it. And we have these in a specific order, and it doesn't really look like the order matters here in terms of these functions. Like, they don't interdepend on each other, right? Every function inside this helper functions conversion, they don't look like they are relying on each other. Otherwise, we would see these colors highlighted somewhere inside the function bodies as well. However, if that is the order we want to use, then we have to stick with it. So tile exponent to max coordinate, tile exponent to diagpix, and then we have diagpix to tile exponent and astpix to diagpix. So we have one of these functions is symmetrical, tilepix to diagpix, or diagpix to tile exponent and tile exponent to diagpix. They're kind of right there. But we can see that these are kind of merged together like that, because we have the tile exponents here. And these are kind of merged together because they're symmetrical. And this one is kind of like, really looks like it would make sense to have the symmetrical version of this, but we don't have a symmetrical version of that. The reason for that is because there's this pigeonhole problem where we can take, this is like a floor function where we take any consecutive integer and we kind of decide which diagonal pixel it fits into. And so we take a lot of numbers and then we funnel them down into these numbers here. So we can't flip this around because there's not there's a many to fewer relationship here. So we can funnel in this direction, but we can't funnel in the opposite direction, if that makes sense. So what I would like to do, though, is because I see everything here, and I obviously see kind of like a need for, there seems like pattern-wise there's something missing here, right? So I would like to say, not that, but diagpix I would like to stub that in as a thing that says, hey, we don't exist here, and there's a reason for it, right? Also, tile exponent to max coordinate, same thing. Just say, hey, there's no such function, and that way, is that going to clutter things up, or let's think about it. Sure, let's just do it, because then everything kind of merges together nicely. And we could make more little stub functions of things that don't exist, but let's just put that one in there, because I know we were kind of thinking about that. Because it is nice to have like a way to test things with like a back and forth function, but sometimes you just can't make functions for things. So right down here, we have astpix to diagpix. And what was astpix? Let's check that out. Offset subtile pixels. Okay, yeah, that's what okay. So over here, we're going to take this, and we're going to take this function and say, you know, U08 AAC 2020, PAINT5D. And it would be, if we were to make this function, it would be diagpix over here. Right. And we'll just make a note that, you know, no such function, right? We'll just say, you know, error. And then we can also make a note that this here is a one-way conversion. Cannot make this function because is a one-way conversion. Right, so it's a one-way conversion, and that is why we cannot create this function. So at vid IID and 0 hours, 26 minutes, and 24 seconds. Let me get rid of this. Okay. So, like I said, I want to make note of what we don't do as well as what we do, right? Because a lot of times you see what's done, but then you don't also see all the decisions that were not made. And this is kind of like showcasing some of the decisions that we absolutely did not make. Okay. Let's go to kind of find the section for these helper functions, and these are helper functions conversion, right? So in here, we should create another section, and we're going to call it helper functions conversion. And let's just add, like, if we want this to really balance out, let's just put 2 colons there, and that'll make it kind of balance. And this put get doesn't belong there. Glockpix to painpix, that doesn't belong. Or does it? Hold on, let's see what we wrote. Well, I mean, well, it's these are conversions. These are conversions, but they're not helper conversion functions, if that makes sense. So let's take this, paste it over here. So yeah, now we have our helper functions conversion. We see we got like 3 things here, but then we have a whole bunch of other things here. So let's kind of reorder this. So we see the max coordinate thing. It's going to go up here. The diagpix to tile exponent. Okay, but then we have astpix to diagpix. So let's just highlight what's here. So we have this diagpix to tile exponent. That is this thing right here. So let's highlight that. And these are in the correct orders, respective to each other. And then astpix to diagpix, right? So astpix to diagpix, astpix to diagpix. So let's insert this. This doesn't actually exist. So let's just say DNE. We're going to just do at DNE for at does not exist. And now we have this thing. So let's color this. And then we have one thing between this blue and orange, or this cyan and orange. So you can paste this, and this is the function we want to write. So PAINT5D. Okay, so that's the function we want. And if we color these, we should probably see them kind of somewhere, you know, where it makes sense. And I know we're missing some of these functions, right? Especially the one we just kind of stubbed in there. Actually seeing where... So we have the cyan here. We have the orange. We have the cyan and the yellow, but I don't see the orange. First of all, let's do cyan. Tile exponent to diag pix. Okay, hold on. So that's in this order. To diag pix, this is the same order. Converting to tile exponent, also there. And then the last thing here is this diag pix. So let's make sure that all these kind of things are accounted for and see what we're missing. So we have these 4 colors here. And if we kind of scroll down through all our code, our just ridiculous amount of code here, we can see we kind of put the oldest functions, we kind of like inverted the order here. Right, we put the oldest functions first, and we can see we have kind of this test code for 2 out of 4 of these things. And hold on. Okay. So yeah, we have 2 out of 4 of these things. I'm actually surprised we don't have... I'm actually surprised I'm missing 2 of them. I mean, we're all over the place, so it's not super surprising that we're missing that, but I'm a little surprised. So, I mean, now that we know that that's missing, right, we can kind of like put that in there, right? We can kind of group these. So these tests are a little smattered around. But let's try to preserve the order of at least the sections. So let's write a little bit of unit test code for this. So AAC 2020 PAINT5D unit test code, and this is going to be called, it's going to be the orange, so it's going to be tile exponent converted to diag pix, and this will be void. And let's make sure that that's actually there. Let's make sure that we type that correctly, that that's actually a thing, that the reason we can, yeah, so it's in the middle where we want it to be. And then we have this thing that does not exist. So we can kind of still say, you know, at DNE. Alright, so we can still say that, you know, this does not exist. And then the next thing is this guy. So we can kind of take these. We're all over the place, and that kind of sucks that we're all over the place like this, but let's just keep on going and try to eventually get to a point where everything starts to come together and we're not like so all over the place. But for now, it's just going to be complete chaos. And we just have to not stress over it too much. Though it is kind of hard with my personality not to stress over this kind of stuff. But yeah, the chaos and disorganization, I do hate it, but we just need to cope with it. Okay, so we have these 4 functions. The 4 unit test. Oh, this already says unit test code, doesn't it? So this, here it is here, then here it is here. So it's like paired unit test, huh? Oh wait, no, these are... Oh, no. This is not paired unit test, this is just randomly kind of here. So let's take this for a second. And this goes down here. Let's put this down here. Okay. And then let's make sure that everything else is not duplicated as well. So there's that. Before we try to write more test code, let's make absolutely sure the test does not already exist, because that would suck. So like right here, let's make sure that that doesn't actually already exist somewhere and we just kind of like lost track of it. Now if it's already the code there, then we didn't lose track of anything, so we're good. Let's make a note of what these are though, right? So we can see these are helper functions conversion, so why not kind of like relabel that again, right? So we want to regroup these again in this kind of same section here. And we can just say, you know, we have, this is our unit test code section, and I'm thinking that we need some type of pattern that's different than what we've been using. And we're running out of indentation space, so I'm going to kind of cut this in half like this, because there's a lot of functions. And I know this is unit test code, so we could just say, you know, I don't know. I don't know what we want to do. We could... I don't know. I don't know what I want to do here, but I just know that this is kind of like... We want some type of section divider here. Here, let's, we want the section divider to be different than what it is up above. So, I don't know, we could do something like that. It's different, alright. It doesn't completely cut off the section, right, because it kind of has these dashes, but it's also very bold, saying that it's a big section of functions. I don't know, but we want something to mark these sections. Because they're all, right, because we already know they belong to this kind of category here. It's just that this is still inside of a unit test, so... right, we have this indentation level here, and we're kind of breaking that indentation level here. But we really do want some type of way to make note of this. So we might actually want to do this, maybe? I don't know. Yeah, let's do something like this. Helper functions conversion. Like, write it like that. And then we can take this and just paste it over here. Yeah, so helper functions, conversion. It's a little weird the way we did that, but I think that there's a little bit of art in the way I do this, and the way I kind of make these sections, so I can kind of wrap my head around what's in here, right? Because we got a lot of stuff in one file, and we don't want to get lost. Sure. Also, if we do colon conversion, I don't think we're going to be able to find stuff, right? Because I think we... Oh, okay, because we use the 2 colons here. Okay, if that, that's how we did it there. And then... Let's make this lower... let's make that lowercase, I don't know. It's lowercase, it's not going to conflict with this uppercase section, I think. But it still is kind of weird. Okay, so tile exponent to diagonal pixels. And the other function that does not exist, it's right here at DNE. Let's look at the diagram and see, well, what do we need to do to test this? So we have some notes here. Really, I want to look at this data file and be like, okay, what's tile exponent and what is diagpix? So we can look through these diagrams and be like, oh, here's diagpix, found that. And the tile exponent is the size of these different things here, right? So I already know what the values for this should be. So we can just kind of like code those in, I guess. So if we do AAC, or let's just do this, because we've been doing this. We did this a few times, and I think I liked it, where we do define function, the function we're testing. And AAC 2020 PAINT5D, right? And then tile exponent to that. Now, I believe these are private functions, so they are lowercase. Yeah, we see this lowercase here. And then after we're done kind of testing this, we can undef the function that we are kind of testing, right? So tile exponent to diagonal pixels. So really all that should be happening here is, you know, let's do a little test table, even though it's kind of like unnecessary, but let's have some fun and try to enjoy ourselves here. So let's do an int16 called table of unit test code, and it'll have, I don't know, so many things in here, something times something here, and then we initialize it with some data. And all we need to do is say that there's a tile exponent and then a value. All right, tile exponent to diagpix. So there's 0, and 0 is going to be mapped to 0. When we use the next one up is 1, and 1 is going to be mapped to 128. So I'm looking at the diagonals here. So this diagonal here to here to here, all these things that are the D's here. So let's make a note of when we're writing this, right? So at vid iid, because I'm thinking that, you know, we might actually forget about what our train of thought was later, and then when we try to run this code later and run these tests and they start failing on us and we don't know what we were thinking at that time, we might want to know what we were thinking when we started creating entries for tab UTC below, right? So we'll make a little note that at this timestamp, if you want to know what we were thinking when we were doing this, then it's going to be right here for you, so that you can know what the heck we were thinking, right? Like, you know, when you have those WTF moments, you're like, what were you thinking? Well, let's have this here to kind of protect us in the future. I'm going to update this timestamp here because it took me a little while to make this comment. So 43 minutes, let's do 44 minutes. 44 minutes and 10 seconds. Okay, so what are we thinking when we are filling out this table here? So we have the diagram over here in PAINT5D data. And this first tile exponent size, the offset to get to these tile exponent sizes, that origin we need, is up here, and that's going to be 0. So when you have tile exponent 0, then you also have an offset of 0. For the next tile size exponent 1, it's these tiles here. And the diagonal you're going to need here is right here, which is a 128 offset. So that's why you have this 128 here. So now the next thing that's going to happen here is things are going to start to get very factorial-ish. So instead of just having another number, we can do 128, and then we're going to add whatever this is, right? And it's going to be half of 128, so it's going to be 64. right? So 128 plus 64, 64, and 64, 128, right? For everything else after that, it's the same kind of deal. 128 plus 64 plus the next smaller square. So we need this origin here, and we have to figure out, or not this origin here, but we want, because we're on this is the fourth thing. So we want, well, yeah, we want this origin here. No, the 1, 2, 3, 1, 2, 3. Okay, so we're not on this one. We're on this one that doesn't actually have any diagram for it. But it's 32. We keep up the same pattern here. So we can do 32 plus 16, and this math should already be in the logic that that this function that we're testing internally, this is the exact logic he uses. But to kind of duplicate it could be a good idea, right? So 1, 2, 3, 4, 5, and 16. And the other thing we could do for redundancy is we could do all of these but collapse the values, right? So just like a little redundancy in the code where it's kind of pointless, but the whole point of tests is to be kind of redundant and do things that are kind of seemingly pointless, because, right, the idea is that, you know, if we're infallible, we wouldn't have to worry about it in the first place. Now, I believe we only want to use exponents 0 to 7, because if we look at somewhere we have, oh, so this is the little table we were looking at. So I know we have this here, right here, for like, why is this a 0 right here? Why is this? Oh, these checksums are, these are 1 through 9, and this is also 1. This is 1 through 8. Like, we can checksum this. So we could do so if we have enough room to where we could actually do this. We have a checksum, but then we also have the indices. And the indices Alright, that's why we're getting confused, because sometimes we're looking at something and we're like, well, is this a checksum or is it an index? So, checksum and index. And you notice this has one more, but when we're actually using this, I do not believe we can actually use this last one. So let's mark this for a second and take a look at the functionality here. I think we might have a guard for this. No, we don't. We don't have a guard for this. But I do believe using that last one would be kind of pointless. But, you know, we are testing it, and that is the thing that would kind of make sense. So let's kind of put that in there. 8, and then this is going to be a +1, right? And that also means that all this has to be slid over, doesn't it? And do we even have room if we slide that over? It looks like we have just enough room where we can kind of squeeze this in here. We can move this checksum notation here. And we can move this over here. And I'm noticing this is 7, 8, this is 9. And this is 8 over here, so... Alright, so now these numbers over here match. The next thing I want to do is I want to take all this and I'm going to take all of it and I'm going to paste it again. We're going to run all of the same tests, except we're going to we're going to collapse it. We're going to collapse what these numbers are. As a little extra redundancy, right? All the values are going to be the same, but it's just an extra redundancy to help protect us. Okay. And there is kind of a visual distinction between these. So, you know, if we want, we might want to kind of like break this apart somehow. I don't know. So the checksum is going to reset, right? Because we got 9 and they've got the same 9. But the index here, the index of the test, is going to keep on growing. So now let's actually just take these and pump them into a calculator and kind of see what those values actually need to be. Let's go over here. Let's put this over here. So you can see that I am kind of using a browser as a calculator. Let's actually go to Google, because Torch, as much as I like Torch, it always tries to hijack the browser. Like, you say, oh, you use Google as the default browser, but then it only uses Google up here, and then sets the home page to some other Yahoo bullshit. And, you know, regardless of what you think of the morality of Google and how they got rid of their do no evil slogan and whatnot, regardless of how good or bad Google is on a moral spectrum, doesn't change the fact that it's the best tool, right? In terms of search engine, because I can kind of like throw anything in here and it works. And so let's do these kind of formulas here. It looks like I have some search results in my Google history that I need to delete because, that's not right. So obviously, first thing is just 0. This is 128. This is actually what we need to solve here. So 192. We're just going to start filling everything out. So 192. And if we run these tests and the first 9 tests pass, but then the next 9 tests fail, that means that we transcribed something improperly. And then we'll have to fix the transcription. But it's good that we have these redundancies, because it's going to protect us from, if somebody meddles around with this, then this also would have to have also been meddled with in the same respect, right? It gives us a little redundancy. And tests are all about being a redundancy to save us, right? It also might be important to be able to recognize these numbers in the future, right? When we're looking at code, these numbers now have some significance. So if you see these specific numbers, we might want to be able to recognize them, right? And be like, 248. That sounds like a, diagonal location in our data. Right? We can already identify powers of 2 really well, but, identifying these numbers that are kind of these, like, factorial powers of 2, we don't really work with these much, so we don't really know what these look like, right? We look at them and they don't look like significant numbers. Now 192 kind of sticks out to me because of the way I blend RGB colors together to get like perfect tertiary colors. But besides that 192, everything else just looks very foreign to me. Yeah. Okay. So now that we have this kind of redundancy in place, right, and we can see that, the last exponent, its origin is at 255. So this is why I'm saying we're not using 8, because the origin here is at the last pixel. So there's only one of them. And so this is the last useful location is the 7 here. And we might want to make a note there that, make a note, that, let's see, what is it? So, 0071. Oh, did I do that thing again? God damn it. And the time is 00 hours, 54 minutes, and 37 seconds. Let me just say, 7 is the last useful index. Okay. because 8 can only store 1 pixel instead of 3 groups of pixels. Right? If you can only store 1 pixel, you obviously can't store 3 groups of pixels. Does that make sense? Now, this video integer ID here, we screwed this up, so this is 0071 here. Oh, no, it's not. Oh, this is not 0071. Oh, God, no. Did we... Oh, no, wait. Okay, good. No, we're good. Okay, we're good. Okay, I was like, oh, God, no, I did the number wrong. No, I'm looking at my files, and I'm like, oh, no, there's a 70, but there's this other thing that hasn't been labeled yet. Oh, that's the video we're currently recording, so no, we're good here. So, we'll get better at this, hopefully, because I'm hoping I'm not going to have a whole bunch of things that say @vidIID, and then, you know, there's not the actual ID of the video, right? So all these things need to be labeled, and if they're not, then that is just going to be trouble for us, right? So it looks like... So right here, right, we have this mystery. See, this is what I'm talking about. Like this, we don't know what this is. It's somewhere between... like, we know PAINT5D was 066. So it's somewhere between 066 to, yesterday was 070. Alright, so if we want to look at that and be like, well, this is PAINT5D. So we don't know what video ID that was. So we'll have to fix this and just say, @vidIID, 0071, time is 0 hours, 56 minutes, and 55 seconds. Be like, we forgot to label the video number below. And let's see, well, what is this? Located on Pix name. Oh, this is today, isn't it? Pix X, Pix Y. Put get. Yeah, we were making this today, so we don't even have to do this, right? We can actually just fix this. This is actually video 71. Okay, so this was the only other place where we made that stupid mistake, and that is kind of... That's scary, because we're trying to make these timestamps to kind of help us out. To be like, hey, here's this code we're writing, here's the actual video of when we wrote that code, and to just help us kind of find things as we're writing them, as we just be able to find, right, we're thinking that the commentary, the comments that we write, may not be enough, and that having the video's timestamps kind of supplement this could really help us. So here we have 9 and 9, that's 18. So we could do 18 times 2, right? Because there's 2 things per test, 2 pieces of data per test, and there's 9 times 2, right? So 18. 9, 9 is 18. So we could also do like this. Since we have those 2 checksums, we could do 9 times 9. Like, to be really safe, we could just do 9 times 9. Or not 9 times 9. 9 times 2, right? Because there's 2 of these 9s. And then, why is this times 2? Well, that makes sense. 9 times 2. And up above here, we could do, and this is rows, and this is, let's call it rows and calls. Rows and calls. This is the number of rows up here. Times the number of columns, right? And kind of space that out and just keep that commentary above it like that. Now that we have this, we can kind of run this test code on it, and we're just going to take the first thing and convert it to the other thing. But before that, we should actually can like, create the variables for tile exponent and whatnot. Now, let's see what the signature for this is. Like, what is it? What does it actually take, right? Because we're messing with a lot of different types here, so we want to make sure we know. So uint 8s is what we're using here. Okay, that's fine. And so now that we know that's what we're using, we can do like a uo8 for the tile exponent, and a uo8 for the diagonal pixels. And these are going to be the expected, or the, well, really what you have is you have actual and expected. So the actual tile exponent goes in, and then expected diagpix is what we are going to get out here. So if we're in some type of loop for dex equals 0, dex is less than or equal to this number here, we can just say number of tests equals, right? Then we can do 9 times 2 times 2. And you can keep that commentary above it. Number of tests. And we could just keep this here as long as these numbers match. I mean, that's kind of odd, right? But then we could do less than or equal to number of tests. Number of tests minus 1. And then dex plus plus. We need to fetch these values. So the actual tile exponent is going to be equal to the table of unit test code plus some type of base index plus a 0 offset. The expected diagpix is going to equal the table unit test code plus some type of base offset plus 1. And then we're going to run the function on the actual tile exponent, and that will give us the actual diagpix. So the actual diagpix is going to be equal to that. So we got the expected diagpix, but then we need the actual diagpix as well. So actual goes into the function, and we get the actual that comes out. So actual in, actual out, and then we have the expected that we want to check against. So then we just say that, you know, if the expected diagpix is not equal to the actual diagpix, then we have some trouble, don't we? We'll just say fail act diag not equal expected diag. And I'm just gonna throw something in there. I'm not gonna worry too much about the error message. I'm hoping this will just pass and that I don't have to worry about this failing at all. But that is somewhat of a bet. So expected and the actual, so the thing coming out of this. So we're going through all of the tests. We have this index here, and we need a right now, let's just do int32 for dex, and this will be current test index. And we also have this base offset value, right? So for the base offset value, let's just do, you know, i32 base offset value for test data. And the base is going to be equal to, what is it going to be equal to? The base equals the dex times, well, there's two columns. There's 2 columns per test, right? So the stride is 2. So all we need to do is multiply everything by 2. Alright, we're going to multiply the test index by stride, and that gives us this base value. So dex times 2 is going to be that base offset, and then first data point, second data point. The first data point is the tile exponent, so tile exponent, and the second data point is the diagonal pixel, right? So we're just extract data. So we could note this, that what we're doing here is extract data from table. We've done this quite a lot. So at vid IID, and we'll do 0071, and the time is 1 hour, 5 minutes, and 21 seconds. So also, quick note here, I haven't done any push-ups today. What does my kind of software say? Do I have like a, if we look at our push-up screen here for a second, push-ups, okay, we're at 0, so that's good. That's what we are supposed to be at, because we haven't done any today. We're just making sure, so we're going to get to that eventually, probably at 2 hours, just because we've been doing things in clusters of 2. So this looks good to me. I'm sure that, you know, somewhere I've probably made some mistakes, but it's good enough to where we can kind of move on. Okay, so let's think about what's here. We have this test, we got that test, we got all these different tests for the section of helper functions conversions, right? And they're all nicely kind of packaged away there. And then we also have these kind of helper functions. And we should probably group those as well, right? Because we had the grouping for, if we go all the way up here to the top, we're going to find the grouping of our unit tests for helper functions generic, right? So we should take helper functions generic, and we should also kind of create a section for that. So I'm going to copy this really quick. And then if we go down to the function, it's min and then the cap, right? So let's make sure that those both appear in that order. And I see we've kind of have them in the opposite order here. Probably because it's the order we wrote them in, or we kind of did it I kind of know why we did it that way, but let's kind of create a section like this, like we did for the last thing. And we just want some type of section divider where it just looks different from our other section dividers, so we can be like, oh, this is probably a section divider for unit test code, right? Just kind of getting a little bit of artsy about it. And we know that this one was above, right? It's this one first, the cap function. It doesn't really matter, but we want to keep a consistent ordering. So even though it doesn't matter, let's try to keep a consistent ordering between this stuff. So we'll take this, and we will move it over. So let's take that, paste it there. Did we almost do it? We almost did it, but we're kind of off here. Or did we just kind of forget to put colons over here? I don't know. So let's look at up here for a second. This divider, helper functions, generic. Oh, I see. So I don't know if that's how we want to do it, but I see we did it here like that. And that also might be an artifact of cutting and pasting. We might have, yeah, sure, I guess that's the way we have it. Well, that's fine. That's fine with me. So helper functions conversion, helper functions generic. And we have the min function test here. All right, we're just we're just putting everything in the same order as a way to help us kind of find stuff. So we have these other tests, these two tests, glockpix to painpix and painpix to glockpix, and I don't know if we okay, so these are like paired unit tests, so we already kind of wrote those. So I'm pretty happy that this is, I mean, we still have kind of stuff that it's still like it's in a paired section, and paired unit tests, and I believe these are like 2 paired unit tests. So we have like a section for paired unit tests for this, and then we have another section of paired unit tests, I think. So if we look at this, glockpix to painpix, is a paired test thing. And no, the main get put test is also in its own section, isn't it? So we're just going to label this as, you know, paired unit tests, I guess. Not worry too much about... Let's not worry too much about the ordering here. Even though... I don't know. Right now, I think we've done enough organization as far as putting things in the order that we think they should be in. And I think we should actually just give a little bit more attention to... making sure... well, actually, no. Let's kind of keep on labeling these because we don't want this section to not have a label. So let's look at what section these are in, if they're in any section. And they're in main get put tests, looks like. So we have put get... Yeah, main get put test. So that's fine if that's what we want to call all this stuff here. I'm fine with that. So let's take all this and kind of indent it and just call it, you know, main get put tests. And then we're just gonna make sure that we spelled that correctly, that we didn't... that this section divider is kind of different, but oh well. Okay, so we have main get put tests. Cool. Okay, so main get put tests, let's make sure that we have that section though. Okay, so we did name it the same thing, main get put tests. Okay, and let's kind of clean this up, right? We've kind of indented a little bit more, so now we kind of have to fix this. And some of this is kind of like out of control now because, right, we have this here, and I think the best way to clean this up is to give us some more room by getting rid of these characters at the beginning and doing like a big multi-line comment rather than this weird, you know, line-by-line kind of multi-line comment that we've been doing. So we're going to remove this like that and then kind of like do that, right? So we have a little bit more room to look at stuff. And then these commentaries kind of are glued together on this. Right, so they're kind of, this whole section looks like kind of a section, so the commentary is a little bit more glued to this code here, which I think is nice. Okay, so now that everything's kind of organized, what are we missing? Because we're all over the place right now. Let's look at this get put test, because I know that's kind of what we started out looking at when we started this stream. So we have the global TX and the global TY, right, with the using the pixel X, pixel Y, right, we're going to go through every single data point. And once we've gone through every single data point, we actually need to test it. And how are we actually going to test this? I believe we're just going to use like some type of back and forth conversion, are we not? And yeah, I think that's the case. Because it's a simple test where we're just testing every single pixel, right? That's like a en masse final test. So we're not actually going to use a lookup table. We're just going to convert back and forth, and then we're going to hope that everything, you know, worked properly, right? So we need to take all these and use them as inputs now. We're going to get these out here, and yeah, we're going to get them out, and we're going to have to just trust that by the time we get to testing this function, we're going to have to just trust that these references are being assigned. And this value here is our input, correct? This is our input, yep, and these are our outputs. So what we could do is let's just take this for a second and flip everything around. And if we flip everything around, we're going to need to use... Right, we can get rid of this, and then make these addresses. And instead of glockpix to painpix, it's going to be painpix to glockpix. And the reason for that is painpix is conceptually these things, and we're not returning them, right? These are inputs, and then glockpixes are outputs, and that's why we have the address operator, so that we can return by output parameter. And if we do this, we can't use the same variable here and here for this global tx, global ty, because then we can't compare them. So we need to think here. This is our actual, and this right here is going to be our expected. Well, hold on. Technically, if we think about it, this value we input here is our actual, and this is our expected. But the terminology for actual and expected is a little bit loose here, because both of these things are generated, right? Usually when you think of actual and expected, you think actual is the thing returned by the function, right? So this would be actual, and expected would be the thing that you're checking, right? But expected is also kind of generated here, right? It's generated in this loop here, and this is our expected here. But expected is also the actual, because we know with absolute certainty that it's the value we want. So the terminology of expected and actual is kind of meaningless in this context. So what we might want to do is say, it's really like, you know, we have, maybe you could say prime, right? GlowTX and GlowTX prime, something like that. Maybe just stick a number on it might make more sense, because actual and expected are kind of meaningless terminologies here. So let's just do this. Let's take this, and let's get two of these going. All right, so, and we can just say, you know, expected and actual are meaningless terminologies, terms for these variables. Could you see if you can kind of cut this, paste it up here, because it looks like we have enough at vid IID 0071. Oh, that's not 0071, and the time is 1 hour, 18 minutes, and 7 seconds. There's no such thing as a negative hour. So let's kind of just throw this here, I guess. Right. And I don't know how we want to do this. Everything's kind of very ugly. We have got some ugly alignment here. I'm thinking we kind of do this, because we have some extra space here. Kind of make that look nice. Sure, why not? So I just want some type of, I want this comment to kind of visually group all of these variables, right? So even though there's the white space between these different clusters here, I want to have this big comment here on this side to kind of visually cluster all that together. Okay. So let's take GlowTX, GlowTY right here, throw that in there like that, right? And then over here, we're going to paste it in there. And let's kind of keep up with our meticulous kind of indentation that people are going to say is a waste of time. And then we know we want the number 2 in here, right? That's going to be returned. This is going to be returned. So this is kind of input here, and this is returned here. We want to just make sure that they match. So now, if 0 or glow tx 001 is not equal to glow tx 002, or same thing for the y, then we failed the test. And we're not going to actually print off anything. We're going to say, you know, unless we actually fail this test, we're not going to go through the extra effort of printing off what went wrong. We're just going to be like error and say get put test failed 2021, isn't it? It's going to take me a while, but okay. So that looks good to me. I'm sure there's some type of mistake I've made somewhere, but we're just going to have to deal with that because we have so many loose ends that we just don't know. We just don't know. We just got so many loose ends. It's all over the place. Well, we see this get thing. That sure looks like a loose end. So if we look at here, is this this is the put test, and if I remember, we wrote this put test, and we cut and pasted some code to get this to work. And we were like, okay, once we get this to work, we're going to cut and paste it, and then we're going to paste it down here and change it around and work that around as well. So let's look at this for a second and see what this looks like. Paint test put, some timestamps for how we did this. The test index, this base offset, the max index, actual values, expected values, input values. Okay, so actual, so we can actually take these, because I see a pattern here. Okay, so we have actuals and expecteds and input values. We can see the quadrant, exponent, layer, location, XY, and the offset dex, and the tile value. And where is that? So tile, we have the tile layer, but where is tile value in here? Because I don't see that. So where is value? So we have the 7, right? So the offset is 7 to get there. And, or the offset's 6. And this says glow TX. So I know we're kind of cutting and pasting to get this to work. So I'm going to guess, is this still kind of a cut and paste? No, that doesn't actually get us anywhere. So I think this test is not yet done. I think we're in the middle of cutting and pasting stuff. And I don't know what thing needs to be done here. This is why we shouldn't have left this half done, because we're looking at this and we're like, that doesn't quite look right. This looks like it matches something else, doesn't it? Okay, so no, that was in the middle of, so we changed that. And, well, let's look at this put function, because I'm going to guess that some of these expected and actuals are wrong, right? I think these are the expected and actuals of a different video. I see you have a time question. So I'm going to guess that we kind of wrote these out, and we never explained them, right? Because we have these question marks, so I think we're in the middle of refactoring these. So what we can do is I'm going to say that this is actually going to be video 71 here for these timestamps. And then we're going to look at our notes for this. So it's the put functions, right? So if we look at our put functions, we see the quadrant, the exponent, the layer, the location. So we have these locations. But then we have this offset, dex, and tile val. So I'm thinking that we just need some more stuff. We got 1, 2, 3, 4, 5, 6, 7. Yeah, we have these 7 things, and look, we have 7 things right here for the put. There's no global here, so I believe that for the other tests we had local and this was global. So if we look at where we kind of cut and pasted from, yeah, we have local and then global, local then global, and now instead of local and global we have local and offset and the value. Okay, so we're kind of getting our bearings, and you know, as confused as we are, this is why we don't want to leave things broken, because this was only yesterday. Imagine how confused we would be if this was like a month later, and it's like, oh, we have this completely broken test. We don't know exactly what it was supposed to do, because it's like, right now it's like a 50-50% merge of some old code and the code we're refactoring it to. And because of that, you can't just look at it and figure out what it was supposed to be. You have to remember what you were doing. And that's why we don't want to leave code in these kind of broken states. And also, this is video 71, isn't it? And we are on PAINT5D Part 6. PAINT5D Part 6. Hold on, I'm changing the video title. Because it's, we are on PAINT5D Part 6. Okay, so now that we can kind of see what we're missing here, we can say, well, with the put and the get, the put has a return value, which I don't think we're going to use. And is this the put test? This is the put test. So we actually have to grab things off of the canvas to get this. So let's, we need to make a note here that we have to, let's make an error here. Error must back up data for tests. Error must use kicksback. So we need to like back up and restore this stuff we're testing. We need to back up all the data, mess around with it, run our tests, and then restore that data. So I'm just making a note here in case I forget about this. And are these... No, these are just inputs. So this in glow whatever, I don't think that's actually necessary. And I see we have all these values here. We have these 6 values. So we can just... Actuals. These are actuals or expected? These are expecteds. I'm not sure how this is actually going to work here. So let's chisel down on this a bit. Let's, like, we might regret this and be like, you know, actually this was wrong. But I think what we really need is just input values. Input values. And do we need diaglopics for this? That's probably still a relevant diagram. But then we need these things. You can actually kind of copy everything from here really quick. We can go. So if we look at diaglopics in PAINT5D really quick. Yeah, I mean, this is a pretty good diagram. The offset ducts is not everything we're going to need for this. What we could do is we could kind of divide this. Oops. And we could make a note of, you know, for one of these, for those variables, that makes sense. But for these other variables, these two, I don't think, though, there's a better diagram probably in here somewhere, right? So it's up at the top, actually, still, isn't it? So I believe this might still be Diaglopix. Oh, no, it's this bigger diagram here, isn't it? And we're gonna call this, do we really kind of dia P5D main? Let's call it dia P5D main, right? So let's kind of like make a little another section for this. And it's the main diagram. The idea of it being the main diagram is saying, hey, this is, when you're trying to figure out what all this means, it's this right here that we want to look at. So we could say bit partitioning. And right over here is the same diagram. And this is space partitioning, right? So now when we see this P5D main, we can kind of see everywhere we're kind of referencing it. And then we can put it in our notes over here. So in our notes, we can say, hey, see this particular diagram for these two variables. Because the idea is that those other variables, we can still use the same commentary, because I think that commentary to understand what these variables mean is good. But then for these other two variables, we have another diagram that kind of will explain that to us, right? So this right here is our tile value. So if we look in our diagrams, we might want to see, do we have tile value anywhere in here? Or do we want to actually put it in, so we only have it in here, but we don't actually have it in a diagram. And it's actually this right here. Like this here is the tile value. So we could kind of say, like, I don't know how I want to say this. We could kind of like create like a section like this and say that right here is the tile value, right? So this thing right here is the tile value. So right here, this is the tile value. Let's get rid of the two pluses so that we can kind of center this and just say that that's the tile value. I don't know how we want to do this. We're getting kind of designy here. But tile value. The tile value is right here. It would kind of benefit from having a little bit of extra space. So maybe, bam, put some space in there. Put another space in there. Backspace, space, space. Then I kind of did like how that lined up, even though it's pointless, but, you know, I'm OCD like that. So yeah, tile value is now kind of in our diagram. Do we want like a little @ symbol? I don't know. But we just want to make sure that when we see tile value, when we see the OSTEX, we have OSTEX over here, and we have the tile value here as well in the diagram. So we can kind of see where those values are coming from when we are looking at the diagram. Okay, so now that we have that kind of put there, we have... did we just cut and paste these? Num test cases put. Let's just make sure this isn't also a cut and paste job here. Num test cases put. No, we already kind of refactored that. That's fine. And right, because we're going to have 4 test cases, right? Number of test cases 4. The number of test columns is 7, right? 7. So that's fine. And for the test table here, the value, we're going to put this value here, and then after we put the value, that's actually the value we're going to expect to get. So these are all inputs, but this final input here is actually an expected value as well, because we're going to do the put and then we're going to do the get, right? Put test, yeah. If we put something, we actually have to get it to see that, hey, is that correct, right? So we can, if we want to put trap values on everything, you know, it's already there for us, so why not just say, oh, put the trap value, and right, instead of tile, this is going to be osdex, right? Osdex, and then the last one's going to be tile value. Let's make sure that that ordering is correct on, like, up here. Osdex, then tile value, osdex, then tile value. Okay, cool. So then we're going to take all of this stuff here, right? A lot of this is just a cut and paste job, where I want to get these values. I want to load them into our unit test code. So we see UO8. Everything is a UO8 here this time, right? Offset dex, tile value, the location TX, right? Because we only needed the global value to have that I16. So we can cast this to UO8 now, because we're using I16 in our inputs. However, I see a problem here. This offset, these indices here are wrong. And that's just because it was taken from a previous test code. And if we see the offset index, it should be like 0 to 15. Yeah, 0 to 15. So we can try this first 0 test. And then we have these different quadrants. That's fine. But then when we're doing the offset index, it would make sense to do maybe, if we really want to set something, I'd say, how about, we could try something like, you know, use 1, set 0, still see if it works. Then use 1 and use the maximum value. So the maximum value of the value is 0, 1, 2, and 3. So we'll use 3. And then use the maximums of everything, right? So the maximums of everything, the offset index is 15, and the maximum value that we can set is 3. All right, so we'll try, those would be kind of like the test that we'll try. Now the quadrants, right, we could also use these quadrants. Let's actually not use these quadrants here. Let's do kind of these basic smoke tests for all of this. So we have 1 and 0, and it also makes sense to have like a 15 and 0. 15 and 0. 1 and 0, 15 and 0, and also this is not the minimum and maximum, right? Because the minimum and maximum is like a 0 and 15, so we could do like a 0. This could be 0 here. So 0, 1, 15, the minimum, maximum, and that's a good little smoke test. So 1, 2, 3, 4, 5, 6, and 7. So we have like 7 of these. I do not like having the same numbers up here, so we're going to kind of like 1, 2, 3, 4, 5, 6, and 7. So we're gonna make something else for a test. Let's say that down here, maybe we take all of this. Let's paste this over here, and let's say that the quadrant is now 1, and the exponent is 1, and the layer is 1, and the location, the x and y location, 1, right? Let's just do everything. Everything is 1s, right? Let's check for some off by 1 errors just by using 1 for everything, and 1 for everything should be a valid value, right? So 1 for the value, right? Everything is in range if we use a 1. So let's just throw that in there, in the mix, and then 1, 2, 3, 4, 5, 6, 7, and 8. So now we have like 8 little tests here, and we're going to for the number of cases, right, this 4, we're going to change that to 8. So we have a little bit more tests for this, for our smoke tests. But, yeah, that's the way we're going to keep it. We could say this, we could comment this as, 8 basic smoke tests. And 0071, and the time is 1 hour, 40 minutes, and 20 seconds. So these are basic smoke tests. And we could just say 8 smoke tests, right? So they're just, the idea is they're just very rudimentary tests to make sure that, everything is working, right? And we'll add more tests later. So, more tests. And we'll do, a AAC 2020 2D Manager. Vital. More tests. Yep. Okay. So we have this test runner here. We're going through every single test index, and if we want to see where those test indexes are coming from, we have a max index here. Number of test cases put, which is now 8, minus 1, because we want a maximum index. And these are 8 tests. 1, 2, 3, 4, 5, 6, 7, 8. So what I'd like to do here, for a little sanity check, is have a way to just see what those numbers are right away. So let's kind of do this, and do a little checksum here. And it is kind of ugly, because we're putting this comment kind of like right in front of everything. But it's going to help us, right? When we want to know like how many tests we have. Now, we might want to say, we have enough room where we could kind of do, a checksum as well as an index. Right, so we could do indexes here. And then we can do an actual checksum over here. And I'm already seeing that we kind of did that wrong because there's no numbers here. So there we go. So we have 8 tests. And if we want to know the test index is over here. And so we're kind of wrecking our formatting doing that, but we're in very tight quarters, so we're going to have to deal with it, right? Now I see this looks misaligned, malaligned. Are we malaligned, or is that just my imagination? It looks a little... something's off. I don't think this was the intention to have it like this. But the ones place... Oh, I see. So this does not match up here anymore, does it? So that's what's going on. So if we want to fix that, we could... let's kind of get this aligned here. Do we want to stick with this? Like, here, let's kind of like put 3 slashes. And so we still kind of have these blank spots here, but we know that at this point we're kind of just relabeling everything so that we can add more tests. So that looks good to me. Now, it is a little bit crazy where we got to look at it and be like, oh god, where are our commas? Everything's kind of busy here. We're like, we got to make sure we don't miss these single characters. But the important thing to me here is seeing these checksums and seeing this kind of table right here. So the next thing I'm seeing is this still isn't aligned, is it? So I think this was the intention to have it like this. Yeah, that looks correct to me. Okay, cool. So that's all fixed up. We have a note to do more tests later. and a little thing that's going to trigger an error if we forget about it later. Going through all the tests, we're setting these trap values. We are getting the pieces of data, so 0 to 6, and there's 7 things here, so that makes sense. Calling the function is something that still needs to be done, because we're actually going to do a put here, right? We're going to put, and we're going to use that, if we look at our notes, put, it's this tile value that we're putting, but we need all this other information to locate where we're putting, right? So we have int 16 of this compared to that. So this looks like we're checking for overflow. And because we have this UO8 cast, and this is a I16 cast. And, right, because everything in here is an int 16. And that's cool. We can do that. I think we can keep that redundancy in here. I think the implicit casting has definitely kind of wrecked our day many times. So let's keep that there. So integer overflow detection. Alright, so that's what this is. And at vid IID 0071, and the time is 1 hour, 46 minutes, and 8 seconds. So the way this works is, right, when we assign these, we downcast them, right? So we want to make sure that these downcasts did not affect it, right? So we're going to take these downcasted variables, and we're going to upcast them, right? But after we upcast them, we're not going to get any of the information we truncated off, right? We're just upcasting them so that we can do a comparison with the original values that are not downcasted, and make sure that they're correct, right? That we still have the quantities still match each other, right? And then we're wrapping everything ridiculously. We got way too many parentheses with ideas. We just want to make absolutely sure that we are doing the logic correctly. So that is our integer overflow detection. Right here is where we're extracting values for the current test. All right, that's what this is. At vid IID. And the time is 1 hour, 47 minutes, and 24 seconds. Right, that's what we're doing here. Okay. So over here, this is just setting trap values, which is kind of obvious, right? And this is 1 hour, 47 minutes, and 53 seconds. We're setting the trap values to make sure that, you know, if we forgot anything, if we forgot to load any of these variables that are up here, we're going to see these bogus values that should kind of draw our attention. Now, I think these trap values may be out of range, though. So if we look at these look like they're supposed to be 8-bit values, right? And if we look up here, we see 8-bit. Now, I think that this is artifact of having cut and pasted, so I think that everything else should be okay, but I'm not sure. So let's just do, you know, these trap values aren't going to be as useful because of the limited range of 0 to 255, but let's just do something at least. And the other thing we want to do is, you know, this is kind of concerning me. And we see at trap values, so maybe we can kind of check out the other trap values of other code really quick and just make sure that the trap values are within the range. So we see these trap values here, the expected tile quadrant, expected whatever, and expected tile quad, expected, so these are out of range as well, aren't they? Because we see the expected and actuals are these 8 bits. Now I see this in thing can be in this kind of range here because it's 16 bits, but everything else is out of range. So we need to do something about that. So we could do, you know, how about just say all our trap values are 255, right? That maximum value. Maybe that will gather our attention, but we said that that might be a little bit too high, where 255 is a very commonly used value. So you might say like 201, 202, 203, 204, 205, something like that. And let's look at where else we're setting trap values and see where else we're setting trap values to invalid ranges. And this would never actually make a bug in our code to where, or something that we're not going to be able to, it's not going to create a problem for us, but it's still improper based on the usage, based on how we define we want to use trap values, right? We want to be able to find these values in the code, but if we integer overflow with our trap values, we're not going to be able to find them in the code. So 8 bits here again, and we got the 11, and this and that, and then over here, 1, 2, 3, 4, 5, 6, 7, yeah, that's fine. Okay, so now we can go back to the code we were actually writing. And we know what that looks like because it has that fancy comment, this thing up here. So we're back where we started. And we can use these, I guess these will be our trap values. Or we could do like 100s. Sure, why not? 100s. And they need to be within the range 0 to 255. So that looks all good. Okay, so now we're calling lockpicks to paintfix, but is that what we want to do here? No, this is our put test. So this stuff here is wrong still. We want to call this put function right over here on this side. So we're going to just shove this in here. Just go, bam, shove that in there. And we got to clean it up a little bit. So we got to indent it correctly. We got to remove the types. And we could try to keep some of this information, but a lot of it is like we could do like we could do sub-quad index, right? So we have enough room there. And then we could get rid of the tile size enum and just say tile exponent. And then the offset index, we could just get rid of that altogether. It's just more information for what that means. Right? And then we can kind of, now you have enough room for that. So cool. So we still have little explanations as to what everything is. And this is the actual value we're putting, right? So this is the value we are putting. And after we put this value, we need to get it. We need to get it and confirm that, hey, we were actually able to put that. We were actually able to put it, and we actually got it, right? So, the problem with this put get test is that if we accidentally use the same exact physical location on the texture to put a value, and we're doing put and then get, put and then get, and put and then get, and we're always putting and getting in the exact same location, say the same memory address would be a rough way to say it. Well, the tests are all going to pass even though they're improper, but that's why we have a get put test later, right? And we should actually think about how we could write this to where we can make sure that that's actually going to pass. So I think the first thing is, let's kind of nuke this for a second and think about, well, how can we make this all pass? And I think the way we can make this all work correctly is we're going to actually do for GP equals 0 and GP is less than or equal to 1, and then GP plus plus, and GP is going to be, so if we're in here, we're going to put it over here, GP get or put loop. Alright. And let's do GP is the get or put loop. And over here we're gonna have this like a double loop here. And I'm gonna explain why we need this get put loop. But Yeah, so this put here, we're going to say that, you know, if GP equals 0, or 0 equals... It really should be PG for put then get. Okay. And so over here where you said GP, I'm going to change my mind here. This is going to be PG for get, and then for put then get, because that's the actual order we want to do things in. You can't get anything unless something was put, right? So I'm going to change this to put or get loop, right? We'll just kind of... Okay, so PG. It's going to be equal to 0 or 1, inclusive, and put get. Okay, so here we're going to do the put, and then the get is kind of the exact same thing, except we kind of have this reference here. And for that, we're going to say that we might want to kind of name these a little bit different. So we could say that this is put tile value, right? We might want to kind of indent it like this so we can kind of see it's a little outlier here. So the put tile value, and then over here, same thing. It's the put tile value. Once again, we're running out of space again. So we can kind of change this a bit. Okay, cool. So where we're declaring these, we need to do kind of the same thing. So the tile value, we have a put tile value. And we have enough room where we can afford to just kind of do this, and we'll be fine. I don't know what we want to do. Since we're kind of up against here, we might want to do that. Yeah, sure. Okay. And now I want to do the get tile value. So this is the output value. So this is 0071, and the time is 1 hour, 57 minutes, and 17 seconds. Okay, so here, we can take kind of this thing here. Let's just paste it all here. So these are, you know, the inputs. Yeah, so we're good there. We can relabel those with the actual time. For the output value, we only have one thing, right? We have the U08 get tile val, or really it's put or put get. Get sounds like a verb. We could call it got tile val. The put tile val and the got tile val. Sure, why not? And then over here, where we're doing the function calls. Oh wait, I think we went too far down. Did we go too far down? Yeah, we went way too far down. So here in this function, we do the put if put get is equal to 0. And then if 1 equals put get, right, then we're going to do the get. And instead of using this put, we're going to use the got tile value. And we see that the signature is basically the same, except this needs to be a pointer, because we're going to return this. So we need to wrap this in like a little address of operator, if we can figure out what button that is. And everything should be the same. So we could just say, you know, ditto right, ditto vars of put. I'm sure there's a better way to say that. But if we can kind of get this kind of in there, I think we can get this in here. We can call this ditto vars of, and then it's the put function here. So, so if we want to know an explanation of what this is, we can just look up here. It's the exact same variables. But I don't know if this is useful here. I think, you know, saying something more like, same exact variables as put function, but last parameter is an output parameter. Right, so you could just say that, and then we could do, you know, @vid IID 0071, and then the time, right? You can put the time here, and 1 hour, or no, 2 hours, and 00 minutes, and 50 seconds. Okay. Yeah, I think that's a little bit better of a description rather than all that redundancy. So yeah, all these same variables in the same order here, except now we're actually going to use the got value. Now I see that everything is kind of not in the same alignment here, so we could move this over, but now we've kind of screwed this over, haven't we? So we can try to see if we can kind of recover that, if we can kind of just smush everything in there, or what we want to do here. Offset tile, subquad index. We could do offset tile subquad index like that. We could kind of make that one kind of big compound word. And then we're really running out of room, but, you know, it's a little closed quarters there. But I think, you know, local tile, we could do local tile like that. There we go. So there we go. So now everything looks kind of nice. The only difference here is put tile value, got tile value. Okay, so now I said we're going to promise to explain what the heck is going on with the put value and the gotten value, right? So we got the put value and we got the got value. Let's kind of highlight those for a second. All right, let's clear all the token highlighting first, and let's highlight these. Okay, so put value, got value. Look over here, put value, set it to a trap, look it up, set that value, get that value. So the reason why we have a put and a get here is we want to put all the values first, and then we want to check all of them. And that's to make absolutely sure that if the memory address for where we're putting everything is exactly the same each time, that we're not going to get a false positive for this test passing. So, you know, all puts before all gets, right? So we'll make a little header here, all puts before all gets. And then we'll also kind of explain, well, what do we mean by that? Why do we have an all puts before all gets? And see if we can kind of make it kind of nice, where we kind of like have this section, and we have a header section about it, right? So @vid IID, and the time is 2 hours, 3 minutes, and 44 seconds. So we do all of the put calls before all of the get calls in case we have overlapping memory / pixel locations where the data is being stored. if we do interlaced get then put if we do interlace get then put calls, we may end up with a false unit test pass. Right, so yeah, if we do the puts and gets interlaced, but every time we store a value, it's always going to the same exact pixel, then we're going to get a false positive where it says the test passes, but really the test should have failed. So we want to do all of the puts first, and then we want to do all of the gets. And let's make sure that we're in the correct order, because we have like this double nesting here. And let's kind of look at this. So the puts and the gets are on the outside, right? So that means that whatever this value is, it's going to be constant for this entire loop. So it's going to be 0 for the first set of loops for ti, and then the next time it's going to be 1, right? So, and if we look at this, 0 is going to be our puts, and 1 is going to be our gets. Now, the next thing we want to do, really quick, is just say that, assert that 1 equals PG, or 0 equals PG. It needs to be one or the other, right? If it's not one or the other, then we have a serious problem on our hand. So we want to make sure that one of these or the others is going to be called. So that looks good. We got this like get put test, and it's I think that's ready to go. The way we kind of wrote this code was a little bit weird because with our brackets here like that, but oh well. Okay, so now we have this get test, and the get test is kind of like, what do we want to do there? Like, what's going to make that get test somehow different from what we've already kind of done? So let's think about what we could do if we're going to say, hey, this is going to be different, right? This is going to be different than what we've already done. So I'm thinking what we could do is I don't know, because we got this put in this get. What's the get gonna do that's gonna be different? And I really don't know, but I need to take a break, so I'm gonna think about this before I come back. Maybe if I have enough time, I'm going to do like push-ups, but we're going to think about what that needs to be. So I don't know how could this get test be different than our kind of put test here, right? Because this is our put test. What are we going to do differently over here? So I'll think about it, and I'll be back. 13, 14, 15, 16, 17, 18, 19, 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Good. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay. So I figured out what I need to do for those tests, but I still got a little break time, so YouTube or whatever, I guess. Okay. So I have an idea for what we want to do for this test, for the get test. We're gonna do something very, we're gonna dig in really deep into the data, and to do this, so what we're gonna do is, we're gonna use this get function here. But we're going to, we need this tile value. We're going to set this up in such a way that Well, we'll just show you. We're gonna dig in here really deep though. So, tile quadrant. 1, 2. It's like 7 things here, I think. Okay. So we're gonna like meddle really deep in the data. So I'm just gonna make a section divider called meddling test number 1. And we're only gonna do one of these because it's gonna take a lot of like getting into the headspace here. It's gonna be kind of complicated, and we don't want to half finish these tests and then have to come back to them later and be like, oh god, what was I thinking? So we want to mitigate that by just making one kind of like very intense test case. But we're also going to do it on the most basic thing we can. So let's go into PixName for a second. So we know the actual data is going to exist here. Okay. So what we can do is we can say PixName, CPU pix 0, and we can set this to some type of value here. And we'll set it to, say we need a, let's set it to, I don't know, we're going to use a hex value. We're going to use something like, you know, 0x, 10, 20, 30, 40, right? So that way we can actually see RGBA, right? And if we set this... Well, this is also incorrect, though, because remember, these are bytes. These are bytes. This is the first byte in that array, and it's RGBA. So actually what we want to do is we just want to set something like, I don't know, how about, you know, say 66, 0x66. In that first byte. Okay, now if that first byte is 0, how are we going to get that out of there, right? How is this all packed in to the data structure? Like, how do we pack that in there? Let's look at our diagrams here. So in PAINT5D, we can kind of see that, you know, we have these 32 bits, and for the offset index, we're doing kind of like this, right? We're taking these like this, or going in that direction. So it would be important to know what bytes we're looking at, right? So we have these 16 things, but what are our actual bytes, right? Our bytes are going to be kind of like these. So if we look at here, we have we're going to have I don't know how I want to do this. So we have 4 things for a byte. So this is R, right? Oh, hold on. Let me think about this. 8 bits. These are bits, right? So 1, 2, 3, 4, 5, 6, 7, 8. So right here, yeah, that is our. So we have R, our R bit. Then our G bit is over here. Okay, R, G, B, and A bits, right? We want to actually see where are these bits or bytes. So R, G, B, and A right here. Okay. So this is 0x66. We need to open up a proper calculator here. Let's open up Microsoft Calculator, and let's look at the hex code, and let's take 66, right? And the decimal is 102, but we see the binary is this. So let's kind of move this over to another screen really quick and say that, you know, assert that 0x66 is equal to decimal 102, right? We want to make sure that that is true. And the binary is 0, 1, 1, 0, 0, 1, 1, 0. Okay, so it kind of has this symmetric pattern here. And if we break that up again, because we know that we need these clusters of 2 bits, so it should be like this. Right, that's what we're going to get, right? 0, 1, 1, 0, 0, 1, 1, 0. So this is our red channel, right? Because this is a red bit right here. Red bits of byte. Red bits. These are red bits. Okay. Now that so yeah, let's keep on looking at this, and also let's make a note here that you know, what's the current time? So let's do like a meddling test. 001, and let's do like a little dash divider so that we can kind of see where we are in all of this. And then we'll just say, you know, at vid IID, it's, where are we? Hold on, let me close this. So 0071, and the time is 2 hours, 31 minutes, and 03 seconds, right? So this is where we are. Okay, so now, hold on. We're doing this get, right? And we want to get the tile value, but before we do that, we actually have to know, well, what are all these locations here? So we're gonna cheat here and do some kind of self-documenting weirdness, you could say. Or you could just say complete nonsense. I don't know what you want to call it, but we're going to do some assignments here. And we're just going to say, equals, well, first of all, we want to get this very first pixel, right? So if we want to get this very first pixel, we know that most of this stuff is going to have to be 0. However, this offset index, if we look at here, how do we do these bits? And we did, right, we have R, G, B, and A, and MSB is over here, LSB is over here. So we want to get these bits over here, right? Because that's all we set is right here, right? So what we might want to do is do something for, you know, R, G, B, and A. Make sure that R, G, B, and A, make sure they are kind of different, right? So we could do this like, I don't know. This is very symmetrical, which kind of bothers me. Also, I'm thinking, you know, it'd be nice to just be able to do this 1, 1, 2, 2, 3, 3, and 4, 4 like that, and say, you know, red bits. Now we're getting a little bit complicated, but green bits. We want to make sure that our bit packing is kind of sound here. And this is alphabet soup. Okay, so 0, 1, 2, and 3, right? That's the way this is working. So instead of these asserts, we're gonna change this around, right? We'll figure out what that is later. But let's figure out 0x11 is equal to something, and let's just assert for all of these things. So I don't know what these are. I just wanted to use these hex values because they have a very obvious kind of pattern in them. I obviously don't want to use zeros here, so this is kind of confusing here because 0, 1, 2, 3, and this is kind of all off by 1 now. We could... Nope, because these are 1 byte values, so we can't exceed that. So we'll take these, and... Right, this is our 2, 2, 3, 3, 4, 4. So let's open up the calculator. And actually, let's just get a browser here, because browser works fine for this. And we just want to do Google. And we're going to just do this to, we're just going to say to decimal, right? This, what is this in decimal? Okay, it's 17. And then what is 0x22 in decimal, right? Okay, 34. Why is it called rule 34? I don't know. 0x33, I was thinking to myself. 0x33. Okay, we got a 51. So we got some nice kind of weird numbers in decimal, so that's kind of cool. Since this is test code, having kind of like irregular numbers, well, actually, the bit pattern is actually what matters the most. So hopefully the bit patterns aren't too symmetrical in here, but we're gonna find out. So we're just gonna say, you know, 17 to binary. So 17 to bin. I think we can do it to bin, and it knows. Yeah, 17 to bin. Right here. So we can make a note of the binary right here. So bin, and we actually want to put a 0 in front of that, because, right, we're kind of dividing it like this. Now, 34 to bin, we're just going to keep on doing this. See what all, okay, yeah, 34 to bin. So, 34, hex 22. Correct. Okay, cool. And then we're just going to keep on making a little table here of our notes and making sure that everything's in these clusters. Okay, so 51 to bin, so let's see what 51 to binary is. 51 is this thing right down here. And let's do 68 to binary. 68 to binary is this. Okay, cool. So now that we have this, we can kind of split that up, split this one up as well, and hold the heck on here. Why is this? 1, 2, 3, 4, 5, 6, and then 7, 8. Oh, so we just have a whole bunch of zeros, don't we? Okay, I'm just making sure that it wasn't for some... Okay. So this is actually... Okay, so, okay, I see. That actually makes sense. Hold on. So, right, so 1, 2, 3, 4, 5, 6, 7, 8. So this last section over here is mostly zeros for them. But that's fine. That's fine. That makes sense. Now, my next question is, can we kind of like take this and convert it backwards just to make sure? So can we take this and kind of convert it to decimal? Ooh, hold on. To decimal. Let's hope that works. So 17. I'm just meticulously double checking because we don't want these values to be wrong. We don't want to write our test code for values that we absolutely want to make sure that these are correct. So decimal 34, cool. And I don't know if I can kind of keep the space. We're just going to keep on. Okay, so this, 51, cool. How about this one? This is our last one. This is very tedious, but that's the nature of tests, so... Okay, so to decimal. What do we got? We got a 66. Ooh, that's not right. Oh, no. This is 01000100. So that's 68. I don't know why they do it this way. I guess that's kind of helpful. Binary to decimal chart table. Yeah, that's fine. Okay, we got 68. It would be nice if we could have like a binary literal in C. Like C has like almost everything I want, except a binary literal would be nice. However, you know what? I'll forgo binary literals for the sake of keeping C simple. You know, like, sure, there's all these other features I want, but adding new features to C is what'll make it turn into the disaster that is C++. So, even though that's a feature I would like to see in C, I'm going to be, you know what? I get it. Let's not do that, right? Because I guess a binary literal, it would be like, how do you do that? Because the binary literal really would need to, I don't know. Anyways, let's keep on going here. So for our git test, we want to just look at that first pixel, right? So to look at the first pixel, it should be this right here. So first pixel, right? We're going to look at all that to get the first pixel. And then we want to extract different data points out of here, right? We want to say that the offset index, it should be in this order, right? So what we could do is we could say, we do these asserts again, and we could break this apart a bit and say that when we're looking at this, if everything is getting packed in the orders that we think they are, and we're going to expect this to be 15, 14, 13, 12, 11, 10, 9, 8. Alright, because we're going in this direction. And that's the thing, it's kind of confusing because we're the offset index, we decided to go least significant bit to most significant bit, so it's not a the bit order is, we have network, we're using network byte order, but then for the bit order we're doing the MSB to LSB, because that's kind of how we do all of our stuff. And so we want to make sure that we know that when we're ordering this RGBA, that the offset index is actually kind of like ordered in this direction, right? And that's a big consideration, right? So it's important that we have a test that kind of codifies that. So so 15, 14, 13, 12, 8, 09, or not 8, 07, 06, 05, 04. Okay. And then 03, 02, 01, and 0. Okay, so those are our indices. So let's just make a note of here. At vid IID 0071, the time is 2 hours, 42 minutes, and 21 seconds. We're gonna overlay the OS dex over the correct 2-bit pattern it should be paired with. Right? So that's what we're doing. We're kind of making a kind of hackish lookup table. We're redoing those asserts. Okay, now we have to, if we want to do that, we're going to have to go like this. Okay. Okay, so, yeah. The video integer ID, this is 71, and the timestamp here. So, what we're doing is we're just putting these numbers right above the bit pattern here. And to figure out this bit pattern, we're looking at this little diagram right here in PAINT5D.d, the data file. And you'll notice that we're going least significant bit to most significant bit to get the indexing. And you see the red byte, the green byte, the blue byte, and the alpha byte right here. And this is all one single pixel right here, right? So this is one single pixel, and we're going to set the first pixel here, right? This is the first pixel, and for the OSDEX, we want to, for the offset dex, we want to kind of get 0, 1, 2, 3. We want to get all of these, right? So, and then we want to check against what the tile value we expect is. So we should make some type of lookup table for this. So we have this like meddling test, and it's actually kind of like getting kind of more intense than I thought it would be. But we're going to make this kind of test kind of self-encapsulating, even though it looks like we're going to need a mini test runner for all of these test cases, because I don't want to do a get, and a get for all of this when we really just want to call it over and over again for each one of these cases. So let's use, let's say that, you know, U08 table I don't know. Let's say table 01. Sure, why not? And this is going to have what's it going to have in it? I guess it's going to have we want to loop and say here's the offset index, and then we want the offset index, and then we want the actual bit pattern, right? Yeah, so we'll say that we need 16 times 2. We need 32 things in here, right? I guess we could do 16 times 2. Okay. So for here, let's do inputs, outputs. So the input is going to be, okay, here's your offset index. And the expected output is just 0, right? And yeah. So we might want to make a note of this is, you know, the offset dex. Just gonna make this 0x0 like that, just so I can kind of, not like that. And that's kind of misleading because it's only a byte value about that big. So the offset dex and the tile value. And the tile value is only two bits. So for the first thing, it's 0 and 0. We can obviously see that. For the next thing, we can see that the bit pattern is just a 1. So that's cool. That's easy, right? So when we do 1, the bit pattern is also a 1. And we can keep on going. So when we have a 2, right, we're looking at this index, this 2, we can see that we have a 0. And when we have a 3, we can see that the bit pattern is now just a 1. And we put 2 zeros here. That could be, well, octal 0 is the same thing as a decimal 0, so that'd be fine. And we're going to keep on going, and we can kind of see that we have this pattern of needing to put something here every single time. So let's kind of duplicate this. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? We need to go all the way to 15. Let's just do 5, 6, 7, 8, 9, and this is going to be 10. And let's put a 1 on each one of these. 11, 12, 13, 14, and 15. Okay, there. So we have a little bit less typing to do as we kind of figure out what all the values should be here. So this 4, right here, it's a 1 and a 1. So the maximum value is a 3, right? And we could also make a note here, right? So why is this? Why is this? What? Why? Why is it that? So we could say, you know, 3 equals bin, you know, bin, right? If we want to make a note of, like, what the heck, what's that all about? It's really the only value we have to do that for. No, the 2 as well is going to be kind of tricky. So 5, let's look at 5, and it might be a little bit easier if we can actually quickly look at these. And so if we do something like this, right, because we have this double-digit indices over here, if we also use double-digit indices over here, then when we highlight these, when we click these numbers here, we can see them in our little table, right? And that's going to be helpful. So we're gonna put this here like that, and everything is kind of getting kind of like ugly. And 3 is bin whatever, so we could just do 3 is bin 11 like that. And get rid of maybe these extra asterisks, and that's kind of all right. There we go. So like that, that'll work. Okay, so now this 5th thing, and we can kind of highlight it. We can kind of highlight everything as we're going through it. The 5th thing is just 0, so we can just go 0. Okay, this 6th thing right here is 1 and 1, so that's going to be a 3. This 7th thing right here is a whole bunch of zeros. This 8th thing right here is just a 1 and a 0, which makes it a 2. Let's make a note of that, right? Because that's 2. We don't know our binary that well, but 2 should be a 1 and a 0. Because we got 0, 1, 2, and 3, and that's 4 bits. 0, 1, 2, and 3 is 4 bits. And the way to think about that is 2, how do you do that? 2, 4, like when you're counting the bits, 2, 4, 8, 16, 32. So if it's just 1 bit, you got 2, and if it's 2 bits, you got 4, because 2, 4, right? And you have to remember that that's the number of values, it's not the highest value. So 4, if that's the number of values, 4 is the number of values, you got to subtract 1 because the range is 0 to 3, right? And that's why if you have 1 bit, you say 2, but it can either be 0 or 1, right? Because 0 and 1 is 2 values. So let's look at 9 here now. So 9 is also a 0, cool. The 10 is a 2. The 11 is another 0. The 12 is another 1. The 13 is a 0. The 14 is a 1. And the 15 is a 0. So this is kind of nerve-wracking, because look at this just craziness here. But it's going to give us a lot of confidence that, you know, we might also want to make a note here that, you know, 1 is binary, right? And do we have everything? Do we have like 1, 2, and we got 1, 2, 3, and then we also have this 0 here. We have like everything here. We got everything we need here. So, you know, 0, it's going to be bin 0, 0. Right, we're not going to comment everything. We just want to comment at least one of them. So we have all the unique bit patterns here. So 1, 3, 2, 1. We got all of them. And if we highlight any of these bit patterns, we see none of them overlap, right? All of these bit patterns, we can confirm they're unique, and they cover the whole range of 0, 1, 2, and 3. Kind of scattered, but oh well. So there we go. So we got this kind of way too intensive a test for just this one location, right? So, so we can say, you know, the first meddling test using table tab 001 only looks at data we set on the very first pixel. This is because we want to confirm our bit shifting logic and our bit shifting packing logic is correct, and don't want the mistake in this test to be looking at the wrong pixel location. Okay, so let's make a note of what time this is. So at vid iid 0071, and the time is 2 hours, 54 minutes, and let's say 40 seconds. Okay. So this is, let's make this look a little bit better. And then we're going to explain what we're talking about here. And it should kind of already be obvious. Well, maybe not. I don't know. I mean, it's obvious to me because I'm in this headspace here. But if you're on looking, what I'm doing is probably complete, like, magic, right? Okay. So let's move this timestamp up a little bit. So 55 and say 55:20. Okay. So this first test, we just want to make sure that the first pixel is just 0. And when we look at the math for how this is done, we're pretty sure that all of this math will get the very first pixel. If this is 0 and the exponent size is 0, then we're inside this block here. And if the tile layer is 0, well, this is tile layer 0, so we're still in this block. And then if the local tx and ty is also 0, then we should be right here, right, at that very first pixel index. And this thing here, the offset dex, we actually want to change this depending on what this test is here. So we actually don't need two things here, right? This offset index is going to just, it's just going to use, right, because you see these indices kind of are, I mean, that's the way we did it, so I guess we'll just stick to it, but you can kind of see that the index in this test kind of matches, it's kind of redundant, but whatever, let's just do it. So offset dex, we're not going to assign this one. I think I kind of stopped in the middle of my explanation here. So, osdex equals the table 001 times the base value plus 0, and then our expected tile value is going to be equal to table 001 and the base plus 1. I kind of screwed that up. Yep. But yeah, so we want to run this kind of like 15 times to go through every one of these things, right? We bit packed 2-bit values into the 32-bit pixel, and these are offset indexes right here, 15 to 0, ordered from least significant byte to most significant byte. So it's kind of ordered backwards, right, in a way. We're using network byte order, which goes this way, right, left to right. Left to right is network byte order, but these are bits, right? And when we're bit packing, this is the way things work, right? For shifting left and right, and when we're talking about the bit indices, this is how that works. Right? If we index these the other way around, I think that would be incorrect. Or at least my mental model of it is this way, and this mental model has always gotten me correct results. I don't know what the consequence of ordering these the other way around would be. Maybe there's no consequence because it's just an ID that you're using, but I suspect it could actually lead to some horrible, horrible problems. At the very least, people looking at it wouldn't be able to understand it because that's not conventional. Okay, so this is table number 1, because it's going to be table number 1 for meddling test number 1. So test table number 01 for meddling test number 001, right? And that's too many D's. So we can make a note of, why is that labeled as that is? At vid iid. And the time is 2 hours, 59 minutes, and 10 seconds. Right, just make a little note of why that is what it is. Okay. So this test table, we got 16 values in it. At any chance that, if we get this wrong though, if we get this 16 wrong and there's not 16 in here, we're going to seg fault. So we got to make sure that's correct, and it looks correct to me. But if we seg fault, once we start running this code, I'll be pretty confident that the seg fault is in one of these test tables where we're fetching an index that doesn't actually exist. Okay, so to calculate this base value, we're gonna need to get the test index. So base equals the test index times 2, right? Because there's 2 items per row. And now we actually need to kind of loop here, because we have all this stuff here, but we don't actually have a loop. So we need to do like a for test index equals 0, and test index is less than or equal to 16, or less than or equal to 15, right? We're going through that like that. Test index plus plus. And another thing we can do, because we have this redundancy, we might as well check it. We need to assert that the test index is equal to that offset dex, right? Because right now, might not be true for other meddling tests, but true for this one. Right, so this is only true for this one because we're only testing a very small, we're just testing this this one pixel right here. It may not be true in other tests, but since we have this big table of stuff, I almost feel like we want to kind of make a copy of this and paste it and just spot check other pixels, right? So right now we're spot checking the easiest pixel we can, the one at 0, 0. We might want to spot check other pixels later and see, hey, does this actually work? And maybe do it in, say, like 4 more tests, like 1 over here somewhere, 1 over here somewhere, 1 over here somewhere, and 1 over here somewhere. And make sure that the X's and Y's are all kind of somewhat different, right? So make sure that we're in like one of these quadrants here, so that the X and Y's for those values are different. But yeah, just some type of other tests. Okay, so test index. We actually need to declare the test index. So over here, we'll kind of create this. So we should TI. I don't think we're going to have over 255 entries in a single test. So I think we can do this. And let's do it like this. So TI, it's going to be test index. And this will be the base and the base offset. Base offset to test data. Test. Okay, and this tile value, right? We don't want to actually use tile value. We want to use this right here is going to be, we got expected tile value, and this one's going to be, guess what? Actual tile value, right? So we're going to use actual tile value and expected tile value for what I would assume are pretty obvious reasons. So this right here, we're not going to use tile value, we're going to use expected tile value, and then we're going to use actual tile value. And if we want to be able to find these, we can have it like this, right? So when we click this, these don't light up. But now if we click these, we can kind of see where tile value is referenced in the code in other places, and kind of be able to scan through the code very quickly and see where all of these different pieces are connected. Okay, so where are we? And also, yeah, where are we and what do we got to do here? So looking stuff up in the table with the space offset multiplied by 2 because there's 2 elements, right? So 2 columns per test. Let's just call it, let's just kind of, yeah, 2 columns per test. That is why we have the 2 right there, in case that didn't make sense. The indentation is a little bit wonky here. I don't care, that's fine. It's a little bit weird. This kind of breaks up the scope a little bit, but it's not, it is kind of annoying me a little bit though. Let's just, oh, I see kind of why I did it that way though. I don't know. Let's just keep it this way. It is kind of weird. Okay, so this offset dex, we're fetching it here. The expected tile value is what we're going to check. So, okay, so now we're going to just do this. You know, if the expected tile value is not equal to the actual tile value, then, you know, error meddling tests number 001, right? So that's what we're going to call it. Okay, cool. So we have a little test runner for this, and we want to write more of these later. So let's make a little section here and say, you know, test with another pixel. So I want to test with another pixel. And we could also make a note of what we mean by test by another pixel, in case when we come back to this and however long it takes to get back here, that we know what we mean by test with another pixel. So at vid_iid and 3 hours, 6 minutes, and 49 seconds. Now that we know our bit shifting math is working, test with a pixel that is not at 0, 0 on our bitmap to verify things are in the, to verify physical locations of pixel data are also correct. And this is a little bit redundant because other tests already kind of cover this, but to have this kind of redundancy is nice, right? Because tests should be redundant, so we're not going to be like, oh, well, another test already did that. No, we're going to have that redundancy, because you'd be surprised how it's like you think you already checked something, and then you write another test for just, like, good measure, and then, holy crap, you find a whole bunch of bugs, and you're like, oh, God, like, I can't believe that I wrote all these tests, and I was like, oh, I'm done writing tests. I've written way more tests than I need, but, oh, let's just do one more. And then you do that one more, and you find problems, and, yeah, it's, I ran into that, earlier in, the Tau sync, I believe. I had that problem. So, writing test code is good. Most of this code base is going to be test code, unfortunately, because we absolutely want to make sure that it's on a solid foundation. So, right, a lot of stuff just needs to be test code. You know, as things become more game mechanic-y, or things that just can't be tested that need to be visually confirmed, maybe we'll have less test code, or maybe we'll have to figure out ways to write test code in our shaders and whatnot. I don't know, but right now most of this is going to be test code. So, what do we need to do now? I mean, that's good there. So, what we could do now is we could kind of just scroll through here and be like, where do we put any other smatterings of just blah blah blahs, right? Because we kind of, as we were writing this, we were like, oh no, we got all these loose ends, let's just kind of pepper in some mistakes and whatnot, and then try to figure out where we left off. God, there's so much stuff in here. Okay. Yeah, so I think we're ready to just give it a chance. We're ready to try to compile it and see kind of what mistakes we've made. And I'm going to expect that we're going to have a lot of mistakes, and we're going to have to fix things, and it could be like, we haven't tried to recompile this in a day or so, right? So the potential for mistakes, it could be like, could take an hour or 2 hours just to go through this and find all the little places we screwed up. But I still hold to doing it this way just because our flow of how we thought about things, we didn't have to have our flow interrupted by syntax checking the whole time, right? We got to think about it pretty clearly. And now, yeah, we got all this stuff, and we need to figure out any mistakes. So there are some obvious things that need to be done here. For instance, let's kind of solve some of the obvious things first. So we have this as a section here. So let's kind of stick to that and say we got this int 08, and we have u32, but we also need like u08, i16, u16. I almost guarantee that we're going to need those in here. And this is this glued to our unit test? Unit test, yeah. So we're going to need a lot more stuff for this unit test stuff. And let's kind of cover our bases on the basic stuff. And then anything else we'll kind of... Let's just do define... So let's define u08. Let's just do all of them. So define i16, define u16, define i32, define u32. I don't even know if I need all these, but we might as well just cover them all. Oh, we even have that right there. So u32, let's just do it in the correct order, though. So we have 8 bits, 16 bits, 32 bits, right? And yeah, let's just use all of them, right? We're gonna... It looks like we are using all of them. There may be some that we're not using, but let's just cover them all right now because it's just nice and organized that way. And this looks kind of ugly. Do we want to justify it like this? Is that what we're doing? But then this can't be justified like that. Whatever. So let's renumber these. And let's check Discord because I thought I heard something. And there's other areas of code that also need kind of these defines. So let's just go down here and paste it. And all we got to do is change the define to undef. And then remove these tokens over here because they're going to say, oh, I see why we did that, because look at that U right there. Okay. Well, too late now. We're just going to have to... Okay, cool. So that's better. What else are we kind of missing in here? Are there any other defines? So this section, I think we have all the defines for this section. There might be something we're missing. But all the most important defines I think we've got. And we're still in the test code. This is a lot of test code, isn't it? It's like test code, test code, test code, test code. The main test function right at the top. Just say, here's all the different categories we're testing. So just a big old unit test kind of thing. And some camera controls, just a lot of stuff. Like this is gonna be a pain, right? This is a huge undertaking. Okay, so let's see. Did we get message? It must have just been on something else on Discord. Okay, so let's give this a few runs and see what kind of mistakes we run into. and see if we can fix what's going on. Well, we got no choice. We got to fix what's going on here. But we're gonna hope that that whatever mistakes we've made aren't too difficult, right? We're gonna hope that it's not what I want. What the hell does alt do? I don't know what that does, and okay. So we actually want window. Go over here. And now we're gonna run this and see what kind of syntax mistakes we made. I know we've made something because very rarely do I not make syntax mistakes. So unknown field PAINT5D TL whatever. So that is a type def. It looks like for our top left, and it's on 282. And it's not where I thought it was gonna be. We must have made changes in a lot of places. Oh boy, this is gonna suck. So this is in Tau Depot data. So let's look at, and we have the file open, right? We kind of kept all the files we were touching open as we were working on stuff. And we see unknown field TL. So we can see P5D TL. And I'm guessing that we kind of added things as we were going, and we probably kind of lost track of some of these things. I also know that I think we need like a TS as well. And I don't know what the TS was for, but I was pretty sure we needed a TS. So, you know, I'm actually going to search the code base for a TS, because I feel like there's probably a TS somewhere as well. So find in files, and we're just going to find all, because I'm pretty sure there's a TS. No? Okay, well, I guess there's not. But yeah, so right here, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 P5D things here. And if we go up to where we have the P5D, we have 1, 2, 3, 4, 5, 6, 7, but we don't have this thing. And this should be, actually it's the tile layer, I bet. Value, exponent, and layer. Yeah, so value, exponent, so that would be layer. So const UO8 P5D TL. And this is going to be the tile layer. Okay. And if we want to know, like, well, where are all these different things, we can say, you know, see this diagram. We're in Tau Depot, yeah. So we can say, you know, see diagram, yeah, that's another thing. See diagram, in file, paint5d.data. And this could change, right? The file that it's in could change eventually. I don't want to change it. I think it's nice having those diagrams in those files like that. But, you know, if we can't find it here, we can find it here, right? So we're going to hope that the commentary that we kind of hard code in here like this does not change, right? Because we don't want to have code, we don't want to have maintenance problems with our comments, right? And the way we're trying to avoid maintenance problems with the comments is have a lot of commentary extracted into this file right here. And anything hard-coded in here, we're hoping it doesn't change relevance. So this diagram here. So if we want to see what these values are, so let's also kind of like make a little diagram here for, you know, @vid IID, and it is, let's see, 0071, and the time is 3 hours, 18 minutes, and 32 seconds. Okay. So let's explain what this. So this is the tile value, this is the tile exponent, and this is the tile layer, and this is in Tau Depot. And Tau Depot is just telling us, what is it telling us? Oh, these are the actual indices for these variables, like where they're actually physically stored on the Tau bitmap. Okay. And if we want to see a diagram of what these represent, we can check this thing here. That'll tell us what they represent. It won't tell us where they are, but it'll tell us what they represent. So we can look at Paint5D, and we can see this diagram here, and we can see like the tile layer, we can see the tile quadrant, we can see the tile exponent, and the value is actually the individual pixel values, and that would be, right, we're going to break apart the 32 bits that make up a pixel and make these 2-bit tile values, right? So tile value right here, we have 4 bits, empty space, a light color, a middle color, and a dark color. So that's what that kind of corresponds to. So we have this little commentary so that you can find me talking about that if you look at this much later. So now I know this was kind of thrown in there after the fact. Does that also mean that this doesn't exist? So let's kind of color these, like, let's say, just color these in order with our token highlighting, and then make sure that that yellow is represented. So the yellow is represented here, but is it represented up here? And oh, it is. So we have that there. It was just we were missing the other thing. We got consecutive numbers. That's good. Okay, so let's give this another shot. So I think we fixed that problem. And let's see what the next problem is. Unknown type name, U08, so that's a pretty easy one to fix. So in Paint5D.data, so it's in our data file. So let's look at our data file for Paint5D. And on line 313, so all the way down here, we gotta figure out what section we're in here. So we're in some type of section called Paint5D data. And that's fine. We can, yeah, Paint5D data. That's the actual, so it's Paint5D data with the Paint5D data section, which that's kind of confusing, but I get it. I get what that means. I'm not completely lost. So you notice that we put the important variables. We actually, the variables take a back seat to the diagrams in terms of the data file. And I was thinking of the hierarchy of that, of like, what do I really want to look at, right? And there's that term of like, you know, show me your code and I'll have no clue what you're doing. Show me your data and I won't need to see your code. I think sometimes show me your diagrams and I won't need to see your data in a lot of ways. So the diagrams seem to be the most important because it helps you get the easiest. It's the easiest way to load a mental model of what's actually going on. So I put the diagrams first. That's intentional. But we have some types in here somewhere. Oh yeah, we got a U08 right here. Do we have any other types, or is it just that? It looks like it's just that. So we can kind of glue our defines where we usually put them. So define U08 right here. And yeah, a lot of this is just going to be kind of simple cleanup, right? Where we're just mindlessly kind of going through places and cleaning up places where we forgot to like put stuff, right? And which is nice because it gives us a little mental break from writing all of that test code all over the place. Extra, so we wrote a function and we put the extra, or we wrote a table. So I like to do this, but strict compilation says no, you can't do that, so we gotta get rid of that. Yeah, so I expect a lot of these are just going to be continuous little mistake after little mistake, and this is just going to nickel and dime us. So this is in the function file. In 258, we have some type of problem. So in 258 over here, we have a problem. So int 16 less than or equal to something something. What does it say? We have a problem with our bracket balancing. Oh, and can we see it? We can see it right here, right? So we wanted to put this kind of embedded with the assignment, but we forgot to close it off. Okay, cool. Yeah, so a lot of this is just going to be painstakingly going through here and finding stupid mistakes we made because we were like all over the place. And the most important thing was to get the general thought process down, right? Get the general thought process down, and if we made little mistakes, we didn't really want that to take away our mental energy. And that's why we have all these little mistakes, is because these little mistakes here are easily correctable. But if we had some big overall picture thing that we missed, if we had some mistake there, the compiler is not going to have any way to check for forgetting about the big overall picture. So we focused on the big overall picture, and we made a lot of little mistakes on the little things, and that's okay. That's just the way we did it. So this is at 301. So 301 right here, you can see, okay, we got a UO8, and we have all these like random defines, but UO8 is not one of them. Do we have any other types in this section besides these 8 bits? Because we might have some other sized types. I'm actually quite surprised, but it looks like there's no other size types. It's all 8-bit logic. That's fine. I mean, that's kind of what I expected. So let's just, define UO8. And also, we can kind of start cleaning stuff up, right? We can say, hey, let's make a little checksum to keep track of how many defines we have in this section, right? So we can start to do some little housekeeping things as we are in this phase of getting stuff at a state where it's going to compile again. And so even though some of this might be kind of, what would you say? A lot of this stuff is kind of stupid. It's kind of like busy work, but we need to make sure it's all there. It's all correct, right? We've added way too much code, and we really should not add this much code between compiling, because if we did anything really stupid, it might be really hard to catch. But sometimes it just happens. Sometimes things spiral out of control like this. So let's give this a run, see what else we got to do. And it's gonna be a lot of busy work here. So assert, and then we have this undeclared I32. Okay, so on 344. We're kind of bouncing all over the place. So on 344, we have this assert, this int32. We have a UO8. Oh, we missed that. Yeah, we missed that. So let's just do define I32. So let's do our shortcut for that. It's the I32. Yep, it's the I32. And 08. You might say, well, if you're doing all these defines, wouldn't it just make sense to like put them all at the top of the file and then not have to do this all the time? And the answer to that is no. And because I've done this many times, and if you try to put all your defines at the top of the file, it just gets out of hand and out of control really quickly. So even though this might be a little microcosm of out of control, like 2 orders of magnitude worse at least. So take this, double it, and then double it again, at the very least. Maybe even more orders of magnitude than that. Or, not double it twice, because I'm saying that, if there's 10 of these, I'm saying 2 orders of magnitude, so I'm saying in the thousands. So, that might be a little exaggerated. I guess 1 order of magnitude. So if you have like 10 of these, then you're going to have like 100 at the top of the file, right? If you try to consolidate everything at the top of the file, it just gets out of hand really quickly. So maybe not 2 orders of magnitude, maybe like 1 order of magnitude. But the idea is it becomes much more unruly when you try to consolidate it all at the top of the file. So implicit declaration of function error 362. So let's go look at 362. What we're going to hope is that as we go through here, the errors get closer and closer to the bottom of the file, but it looks like things are being, I don't know. I'm not sure how the preprocessor does this, because it seems to be bouncing back and forth. So we see this default, and then we see this error. So the problem is this macro probably doesn't exist. So if we look up here, we got this, we got that, we got all that. We got all that stuff, but we don't have the actual error. And so we need to, define the error message. That's going to be AAC 2020 PAINT5D and halt. Okay. And then down at the bottom, we got to undefine that as well. So duplicate this, change this to ERR for error, make that a 9, right? And in a lot of sections, we use that halt function thing. It might not be a bad idea to say that error should be like at the top of the file, but this is the pattern we're doing. We don't want to break the regularity of the code, even though it does logically make sense that error is one of those special macros that we might want to put at the top of the file, but like I said, it's a slippery slope putting stuff at the top of the file in terms of macros, so I'm not going to do it. Unused parameter diagpics on 379. So let's look at 379 here. And we have this thing, and it looks like error cannot make such function. Okay, so this is just a thing where it's stubbed in here to let us know that we can't actually use it. So we just need a no op for that. Diagpics, and then nop. And we might want to do something like this, at nop for no op. And I don't know if we've done that before. So let's look into our hashtag diagrams here, or our hashtag documentation, and just control F for no op first. Yeah, we can't even find that without the at symbol. So let's just do at no op and make a note of what that's all about, because we've used that in a few places. It would be good to kind of describe, well, what do we mean by that when we have that in the code? So at nop means no operation. Typically, we use this to subvert compiler warnings about having unused variables. Okay, that's what we mean. And then we can do at vid.iid, right? We can take the current video, 71, and the time of 3 hours, 30 minutes, and 38 seconds, or 40 seconds now. Alright, so this is what no op means. It just means that we're trying to subvert the compiler warnings, usually. It just means no operation. Usually we use it to subvert compiler warnings about unused variables. I'm sure it has other uses, but that's mainly the use I use it for. And so right here, this is where we're using this at no op to make sure that we don't get a warning about not using this, because this function is just a stub to say, don't write this function, right? Cannot make such function diagpics to astpics. And if we highlight this, we can see, oh, that's the function. So that's good. So let's try to rerun this and see what we got here. Oh, also this vid thing, what the heck is this? So, oh boy, did we... God damn it. Did we do this today? I don't know if we did this today. Hold on. So I don't know if this was today or not. And because I don't know if it's today or not, we're going to have to say that... we're just going to have to say that the... God, I have to get better at that. So, if we look at what videos we have, it's either 066, the very first video, to now, which is 0071. So we don't know exactly what video it is, but we can narrow this down, this commentary. Like, we made a mistake. We don't know what video that is. Actually, here, what we can do is we can just do another commentary here, right? We forgot about it, but it's still fresh in our head what we wanted this to mean. So why not just say, you know, at this time, 3 hours, 32 minutes, and 30 seconds. Okay, so now let's describe this once again. Cannot make this function because astpix to diagpix is a one-way conversion. Okay, so we're going to stub in this function because we want to also include what we do not do. A lot of times you see what's done, but you do not see what was not done. If we want to kind of expose that proverbial under the water iceberg, right? You see you see a very little amount of the iceberg above water, but a lot of it's like beneath the water. And we want to actually kind of expose some of that stuff that's under that water, some of that hidden stuff. And a lot of the hidden code is the code you intentionally did not write. And so we want to kind of expose that here. So that's why we wrote this function. And why is this a one-way conversion? Well, it's because this is a few to many relationship, and in the other direction it's a many to few relationship. So we're going to take these values and we're going to funnel them down to a few values here. But since we lose information from funneling down a whole bunch of values to a few values, we can't go back the other way, because once we get to diagpics, we lost information and we can't convert back the other way. So there's no way to do a test where we do astpix to diagpics and then take the diagpics output and then pipe that back into a diagpics to astpix function. We can't do that here. because of the information loss. So we can't do like a two-way back and forth conversion test, which are really nice. Like being able to do back and forth conversion tests where you say, you know, A to B, run A to B, and then take the result of A to B and pump it into B to A, and then cross-check the results. That's a very nice way to mass check your conversion functions, right? Piping them into each other. But in this case, because there's information loss when we convert to diag picks, we cannot do one of those back-forth tests, and we want to make absolutely sure that you know, we don't accidentally do that. So because we have information loss when funneling slash converting down to diag picks, we cannot do a back and forth conversion test. Okay. So let's talk about back and forth conversion test. Let's like make a little section for that as well. Okay. So let's do is an easy way to check the validity of a conversion function by piping the output of one conversion function into the inverse conversion function. So let's do an example. So if we have example, you know, func A to B that takes A and it returns this returns B, and if we have func B to A and it takes a B and it returns a returns A, then we can say something like this. We can say A1 equals 5. Now we could say, let's say expected actual A equals 5, and we don't really need an actual A. Expected, let's just do A1. A1 equals 5. A2 equals, not set yet. Yep. And then what we can do is we can go A to B, A1. And then we can say that A2 equals B to A right? We can wrap it like that. And then, you know, if A1 not equal to A2, then fatal error, failed test, right? Right, that's what we're talking about. So back and forth conversion test, this is what we're talking about. Let's just do a, you know, at vid IID for this as well. And 3 hours, 38 minutes, and 30 seconds. Okay. Let's just make that a 40 for now. Let's make it a 40. Okay, so back and forth conversion test. It's just an easy way to check the validity of a conversion function by piping the output of one conversion function into the input of the converse function, or the inverse function, right? So if we have a to b and b to a, we could easily test them by doing a back and forth conversion, right? So we could have an a1 and an a2, and we say a to b, a1, and then we pipe the b of this into the inverse function here to get back the original a, right? So if this a and this a don't match, then we failed the test, because these tests should be able to convert back and forth. Now, with certain tests where there's information loss, where you're like funneling down from a large amount of values to a few amount of values, you won't be able to do something like this. But in this case, if you can do it, it's a nice way to en masse check a ton of values and have like a really good amount of code coverage with very minimal amount of lines of code. So this is really nice if we can do it. But in this section, this thing here, we can't actually do this type of test. So I was just making a note that we cannot do a back and forth conversion test because of information loss, and to not make this function here. Okay, cool. So we've documented that. Let's kind of run this again, and then also check our push-up thing. So our diag picks undeclared first use something something. That is just us not being able to spell. So we did all that work, but there we go. Okay. Let's give this a run. We got like I minus 1 something something undeclared. Okay. And where are we? We're in 420. So 420, we have this I minus 1. This thing is lil, largest index less than. Okay, sure. And this is an index right here. It seems kind of like a pointless variable almost. It's like, why do we have this here like that? Because we're not even using... Are we even using this, or is this just empty scope here? Yeah, this looks completely incomplete, doesn't it? Looks like we kind of like stubbed this out, but this is inside of a scope. If this is then largest index less than equals this for whatever, but there's no function calls in here. There's nothing being tested, and you know, we have this thing here. So the first thing is, well, let's kind of look at this, because there's more problems than just a complete syntax error. It looks like we've kind of missed something here. PAINT5D ASCII picks to diag picks. Okay. Actually, maybe this is not a test function. Never mind. We're going through everything, and if this value is less than something that we're looking up in here, if that's true, then this is the largest index less than, so we're going to store it, and we're going to keep on overwriting it till we find it. So let's actually look for that. So this lookup table right here, it's saying we're going to find the largest thing that we're less than to see where we are, right? So if we're always going to be, we're never going to be less than this, so we're never going to be at index... we're never going to be less than this, right? But this starts out at 0, so that's fine. If we're less than this, it gives us a 1. Well, we're never going to be less than this, so we're going to end up... The first test is saying we're less than this, and we see this as an I minus 1. So... let's do a little assert here that I is greater than or equal to 1, and I is less than or equal to 9. Or actually, not... If we look here, 9, it's actually going to be less than... Right, this one doesn't actually count, because this is like a 1 by 1. This is just 1 pixel. So this slot is never used. This slot's never used. But we could get 9. because then we have 9 minus this 1, which gives us an 8. So we're going to say that that this is the case. Or actually, let's do this assert first. Say should never first comparison should never be true, so we should always have an I of at least 1. Okay. Now that we've made that commentary, we should probably stick to using the variable I, since we've kind of done this to ourselves. And I is not declared. What else is not declared? So we got this, like, lil thing. And for the looping through, oh, we do have I right here. It's right here. However, I believe it only lives in this scope, and it doesn't exist out here. And we use it right here. Why? Well, hold on. Why do we have an I minus 1 here? Is that how we want to do that? Or are we just being, like, weird here? Yeah, that wouldn't be I minus 1, right? Because I loops through everything. So this should be the lil thing, right? This should be lil. And because of that, really, I guess we should only have the I kind of live in here. That way we don't accidentally reference it out of here. Because there's no reason... Yeah, because I would always be that last thing. So we just made a big mistake there. That should be lil. And we'll declare it inlined here so we don't accidentally reference it outside of here. Okay, cool. So we got this U08 and we got this I32. Do we have those here? So we got U08, we got I32. Cool. So yeah, if we want to see the diagram of how that's... so let's make a little video comment here. So at vid IID, and the time is 3 hours, 46 minutes, and 28 seconds, or 30 seconds. Let's make that 40 seconds. Okay, so C diagram, C PAINT5D data, actually want to see file paint5d.d. We want to see this, and we want to see this section here. And if we look at that, and we want to look at this variable right here. So var, okay, and look at this variable. Okay, so if we look at that, and I'm going to actually move the comment up a little bit farther because it took me a while to type that. Okay, so for this commentary, we're going to change this to, where are we? 4750. We'll say that is, we'll change this to 4750. Okay, so, right here, this is where we are. We want to check these files, which is over here. This is the data we want to look at to figure out how this function works. And we're going to loop through I and see, and look at this lookup table and see if, hold on, what's Astapix here? Oh, Astapix is the input. So we want to say, is the input less than these numbers? So if we're less than, then it tells us what diagonal pixel we're in, right? So actually, there's other diagrams we need to look at here, because this kind of describes the algorithm pretty well, right? So if we're less than 128, we're in that 0 to 128 block. And if we're less than 128 plus 64, we should be in that next block that is adding the 64, and the next block, and the next block, and the next block, and the next block. So let's actually see the diagram for that. So the diagram corresponding to what's going on here is this diagram. Well, not this diagram here. I mean, that diagram would do, but this diagram right here. So we see this first diag pix. This is our 0. This is our 128. This is our 128 plus 64, right? So if we are less than 128, then we're inside of this block. If we're less than 0, well, that's impossible because the values can't be negative. So that first condition never gets hit. That's why you have this assert that says lil is greater than or equal to 1, because the 0 condition, that first index should never be hit. But yeah, this is our 128, and then for this next diagonal here, we need to make sure that we are less than 128 plus 64. So if we want to see the 128 plus 64 I'm talking about, we can go down here, and we can see this 128 plus 64. And then we see this progression of adding half every time. Plus 32, half of 32 is 16, half of 16 is 8, etc. Adding half each time. And the reason for that is, once again, if we go up to the correct diagram here, if I can find it again, a lot of these diagrams will do, but I just want to use the appropriate one. So this diagram here, right? So we have this block that's 128, and then we have this like factorial of adding the halves, right? So 128, add the half of 128, then add half of that, and then add half of that, etc., until you get to just adding 1. Okay, so this diagram is actually kind of useful here. So we should also make a note of this diagram, right? So we see C file, C var, and we should also say, diagram, and make a note of the diagram as well, right? So we have all this information of everything you need to look at to be able to understand this code, right? So is that enough? I don't know. I mean, if all these commentaries are not enough, then I don't know what's going to help you. Now, the reason I go overkill with diagrams is because there are many instances where I looked at some code and I had no clue what it did, but then I saw the diagram and I was like, oh yeah, I instantly know what it does. Even if it's been like 3 months later, I look at that diagram and I'm like, boom, instantly know. Whereas if I had to read the code again, then I would have to, it would take me like, 5, 10, 20 minutes probably to figure it all out again sometimes. Now, what you can do is you can look at the diagram, understand the diagram, and then you can look at the code again and to just spot check the code to make sure the code makes sense. Okay, but so we got this. And what do we want to do next? What are we doing next here? Well, we got these UO8s and whatnot, and they are already defined down here. So let's give this another run and see what other mistakes we've made. We've made a lot of mistakes, I'm sure of it. And I would like to, oh boy, restrict. Okay. Before restrict. So let's look at 460. Maybe we're just using restrict in the wrong. So 460. This kind of pointer here, something restrict. I'm gonna guess we didn't put the restrict keyword in the proper place. Maybe it was supposed to be over before the variable name, maybe. So let's actually look that up. So the restrict keyword, I'm guessing that's what we did wrong. Restrict keyword C. So the restrict keyword makes C as fast as Fortran, supposedly. Which is kind of crazy, because people are like, Fortran is an ancient language, why would anyone use it? And it turns out that, supposedly, Fortran is actually faster than C and C++. And for heavy number crunching, it's actually, like, a useful thing. So in the C programming language, after the C99 standard, okay, so we are doing C11. Like, if we want to use restrict, this has to actually be C11. But we did want to stick with C11 anyways, because we wanted access to a coherent memory model, like with atomics. So that's fine. Now let's see how that's used. We see restrict in C. Okay, so the variable name is last, and that restrict keyword kind of goes in the middle. So we just kind of have to take this, and we're going to cut this out, and then we're going to... I guess we can just cut that out and then just paste it in, right? Well, maybe not as easy as that, but let's see. Almost. Okay, so the restrict goes there. Yeah, that's all the mistake we made. I do not use restrict that often, and that's just why it's not, you know, represented. Okay, so now we're getting to stuff that I intentionally put in here to not lose track of stuff. So that's cool. So let's see. Finish this formula. So did we not finish this formula? I'm going to guess that... Oh, boy. So we got all this stuff that we have to look at now. Oh, that sucks. Okay, well, that sucks, but we'll get to it. We'll figure it out. Let's just save our work, right? We're not in it. We're still in a broken state, but let's just... we haven't done this in a few days because we were like, oh, we're in a broken state, don't commit in a broken state, but we've done a lot of work here. So even though we're committing in a broken state, we might as well. We're not gonna push it up to the kanji coder though. We don't want to push up anything broken to kanji coder, but we'll push it up to our private repo. So git status and git add dot and git commit -am broken commit working PAINT5D, right? So this is what we're working on. We make sure that we tag it as a broken commit, so we never try to, like, revert to that part of our code and try to run it, because it's never going to work. So git status. Okay, and git push GitHub master. And also there was something else I wanted to do. I had some other ideas for some other future features for other systems, and I don't want to lose track of those. So I'm going to stub in some stuff while I'm here. I'm still kind of all over the place. But in our oh boy, what time is it? 8:04? Okay. So let's, we should probably do some, it's almost 4 hours, so we should probably do like some push-ups. But let's look at the library chain here. And you might see a little note right down here, to do. And we're also going to do something called, I think we're going to call it quadzom. Quadzom? Yeah. And let's actually kind of like stub in quadzom. These are going to be like far future things that may never be done. But I want like a little footnote of them, because I think that it would be cool, and if we can get them, they'll be these nice to have things. Level geom is definitely going to be a thing, because this is eventually a level editor. This is something where maybe it will be good, maybe it won't be, but it's like a far future kind of thing. But we're going to stub it in anyways, so we're going to do this. We're going to do this, and we're going to say quadzom .d. So this is a nice to have. Nice to have. An editor mode where we can select different quadrants of the loaded level and zoom into exactly that quadrant. Once zoomed into that quadrant, we can then do it all over again, picking another quad to zoom into, until we get deeper and deeper and deeper zoomed. So, for instance, 0, 1, 0, 1, 0, 1 would be a zoom of 4 orders of magnitude. First zooming into top left quadrant, number 0. That from there zooming into top right quadrant, number 1. Then zooming into, from there, zooming into quad number 0. From there, zooming into quad number 1. So this is saying this is depth 0, this is depth 1, this is depth 2, this is depth 3. So this is nesting depth. And this is at stack address. And I don't know if we have an at stack address thing, but let's see if we have a at stack address in here. So if we go f stack address, it is a concept I would like to document if I have not. Stack address, we have not documented that. Okay, so let's do that. At stack address. Okay. An array whose values tells us what quadrant to drill into at a given nesting depth. It is a way to compactly store the location within a quad tree or a quad tree-like structure. Okay. For example, 0. Let's do 0, 2, 3, 1, 2, and can we even have enough room to where we could actually kind of do this? Right? Can we actually kind of... Here, let's do this. Let's let's look at the very bottom depth first. So the very bottom depth, if we want to look at that very bottom depth for a second, and make a nice little diagram here of what we're trying to explain. So this 2 here, 0, 1, and 2. So 2. And the next thing is this 1, right? So what we're going to do is we're going to just paste some stuff. And the 1 should be the second thing here. So we're going to blank this out. And say, you know, because this is the 2 here, 0, 1, and 2. But 1 is going to be 0 and 1, so it's going to be here. Oop. Let's make some more room. We can also delete that. Okay, so this is like that. Let's also kind of get rid of these subdivisions where they don't matter anymore. Clean up this diagram a bit. So right here, this is our... If we wanted to make a note of this, we could say this whole thing right here is our 1. And then if we do this all over again, this 3, 0, 1, 2, and 3, so this is going to be the lower corner now. Copy this. Just paste it. And blank this out. Hold on. 0, 1. This is our 1. What am I doing here? That's wrong. This is our 1. This right here is the 1. My bad. This is our 1 at that given depth. And we only have 1, 1, so that's kind of easy to know what we're looking at. And however, this thing, 3, 0, 1, 2, 3. So it's this, we're saying that it's over here. It's this block over here. So let's kind of, I don't know, let's just cut paste this really quick to get our bearings here. Nope. Nope. Okay. Then we can kind of cut this out, move this around. So this is our 3. Then we can take this line here, and we can kind of paste it over here. That's not quite how I wanted to do it, but this is kind of cumbersome. ASCII diagrams in general are kind of cumbersome, but I like how it's very compact, and it's right there in the source code for you, you know? That's why I like them. So here's our 3. This is our 3 here. You know, this is our 3. We might just want to leave it at that, maybe, because if we do anything else, it's going to be hard to diagram, I think. So like a 3, 1, 2, and then, yeah, let's just call it 3, 1, 2, right? For example, 3, 1, 2, and nesting level equals 0. Nesting level is 1. Just coincidental. And then over here, the nesting level is 2. So that kind of, that's kind of stupid where it kind of all matches. I don't like how that matches like that. But we are kind of like out of room here. So this is quad. This is quad 0. Nlev 0. Nesting level 0, right? And then over here is going to be quad 1. Nesting level 0. And then over here, right, is same deal. Still nesting level 0, but we're at 2. And then finally, this is quad 3, right? So we could actually say that right here, we could take this kind of thing here, and we could just say that the quad is 3, and the nesting level is 0, right? And then for this, we have these different quads. I don't feel like kind of... quadrants, and then you know, we could make a little fake comment here. Nesting levels, and and we'll just call it nlev. And the quadrants, we'll do the quad with the number symbol. Okay, so this is a nice little diagram to kind of explain what I mean when I say a stack address. Right, we just mean like some type of an array where we're storing how to traverse a quad tree or a quad tree-like structure. So we have this little reference here, and next time we're looking for it, hopefully we'll be able to find it. So let's also do like this at stack address, make sure that we didn't kind of like do it this way. And if we did, well, that kind of sucks. Well, we should have been able to find the other one even if we did that. So yeah, at stack address. And yeah, we'll kind of double up this section to have the underscored version as well. Okay. So that's nice. And so let's save quad zom. We could also say zom quad, but the idea is quadrant zoomer, right? And then we have like a game idea. Find the microscopic atomic bomb hidden somewhere in the level, right? Okay. So we're gonna go into the library and we're gonna do quad zom dot d dot underscore. And then we also need to make the function file as well. So quad zom dot f. We're just gonna do a feature I'd like, but a far future system. All right. Okay. So now those are kind of stubbed in there. And now that I've stubbed those in there, let's run this again, right? We're gonna get that error finish this or whatever. Let's make sure we're still on error finish this. Then also we need to do like 20 more of all our stuff. So okay, cool. So let's do a git bash here. Stubbed in far future system. And then also, we should still tag this as a broken commit. It's a bit long, but I think it'll still be okay. Okay, so we should probably do some push-ups, but let's look at what this is for a second and be like, okay, well, what is this function here, first of all? Where are we? Glock picks to pain picks. So let's get ourselves in the correct headspace really quick. First thing is in PAINT5D data, we can find what we mean by that. So Glock picks is some type of global pixel somewhere on this 512 by 512. And we want to get the paint pixels. We want to get the exact tile quadrant, the tile layer, the tile export. We want to get like all of that stuff, like all of this stuff, right? We're returning it. And we want to make sure that we get that math correct. And it looks like we're in the middle of writing it, and then all of a sudden, at some point, we're like, oh god, we have all these other things we need to do, right test over here, right test over there. We kind of lost track of where we were, because everything kind of started to unravel into all these loose ends all over the place. But now that we're kind of back here, we can see that, oh, we left a little thing for us to remember to finish this, so we can finish it. But right now, let's check our like little push-up meter thing here. So push-ups are... so we've only done 20, and we're almost at 4 hours. So we actually need to do like 20 of each of them. Actually, we're over 4 hours, so we need to do 20 of each of these. So we're gonna do 20 more push-ups, 20 more crunches, etc. Let's look at our agenda. PAINT5D, tile, camera, keyboard, inputs. Like all these things are kind of tackling all at once. That's kind of why we're in a big mess right now, because we're doing number 2. we're doing number 3, we're doing number 4, and we're doing number 5, and we decided somehow, for some reason, we're just like tackling all of them at the same time, and that's a horrible, horrible thing to do, but we've already done it to ourselves, so that's what we're stuck with. So, with that, let's do some push-ups. We'll be right back. We're going to do 20 of each, and then if we can do more, we'll do more, maybe 10 more, just to get, because I know we'll end up at 5 hours eventually. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay. Okay, so we got like 30 minutes to 9. Well, hold on. Let's update this for a second. Okay, so I'm gonna take a break and get food or whatever. Because I have to eat for like, yeah, I'm gonna cook some stuff. Let's do like a 30-minute break. Enough time to like cook some food. Think about what needs to be done next. Take a mental break from all of this. And, right, it's 4 hours in. That's half of a workday if we're doing like an hour-long workday. So let's take a break and try to keep on going after. So let's take a break, and then we'll get to finishing this function here. So, break time. Do 32. Okay, so it looks like I have to attend dinner for my mom's birthday, so I'm out of time. So we're just going to stop this recording now. I would rather do this, but we're just going to stop after break anyways. So here's our agenda, and let's see next time. Next time, PAINT5D camera, that's what we're working on. So we'll get to more of that later, but we gotta go. Yeah, so later.